Hello, friend, and welcome to the Sleepy Meteorologist. Tonight, we're gently drifting into the quiet mystery of why some storm clouds look so dark. Not in a hurried way, not in the sharp language of forecasts and warnings, but slowly, like watching the evening sky soften from blue to violet. Maybe your day has been long, or your thoughts are still carrying the soft echoes of the afternoon, the unfinished conversations, the glow of screens, the small weather systems of your own life still swirling. If you're ready to unwind, this is your invitation to rest. How's the sky looking where you are? Is it clear and starlit, brushed with thin silver clouds, or wrapped in a deep, rumbling grey? Wherever you are, imagine stepping outside for a moment. The air cooling, the light fading, a tall cloud rising quietly in the distance, its base turning darker as it gathers rain. If you enjoy these calming meteorology journeys, feel free to like or subscribe. Only if it feels right. For now, you can snuggle in. Let your breath slow. There's nothing you need to solve or figure out. Just listen, and let the sky grow heavy and soft. Let's begin. As we drift into our journey, we begin by exploring how ordinary clouds become storm clouds. At first, a cloud can seem like the gentlest thing in the world. A slow floating thought in the sky, weightless, quiet, and harmless. A small puff of white, hanging lazily above rooftops or open fields. These are often cumulus clouds, the kind that look like soft cotton, shaped by sunlight and warm air. And yet, sometimes, these peaceful clouds begin to change. They don't do it suddenly. They don't rush. They simply grow, little by little, as if the sky itself is slowly breathing in. A gentle cumulus may gather strength, growing taller and darker. Its edges, once bright and smooth, begin to billow upward. The cloud thickens, the base flattens, the top rises higher, swelling into a more dramatic form, like a mountain being quietly built out of mist. And as it grows, it begins to carry more weight than it once did. To understand why, we can start with something simple: the movement of air. The atmosphere is always in motion, even when we can't feel it. Warm air tends to rise because it is lighter than the cooler air around it. This rising motion is called convection, and it's one of the most important ingredients in the story of storm clouds. When sunlight warms the ground during the day, the surface of the earth becomes a gentle heater. The air closest to it warms too, and that air begins to lift upward in invisible columns. You might imagine them like slow elevators of warmth, rising quietly into the sky. As that warm air rises, it expands, because the pressure is lower higher up, and when air expands, it cools. This is a soft and natural rule of the atmosphere. Like a lullaby, the sky repeats again and again. Cooling air can no longer hold as much water vapor, and so the invisible moisture within it begins to condense, turning into tiny droplets suspended in the air. This is where clouds are born, but not all clouds are destined to become storms. For a cloud to grow into something larger, something taller, the rising air must continue to rise. The sky must allow it. The atmosphere must be willing to support the climb. This is where instability comes in. Instability is simply the atmosphere's tendency to encourage upward motion. If the air above is much colder than the air below, warm rising air will keep lifting because it remains warmer and lighter than its surroundings. It doesn't stop. It doesn't settle. It continues upward and upward and upward. And as it rises, more moisture condenses, more droplets form, the cloud expands, Now, the cloud is no longer just a small cumulus. It is becoming a tower. A cloud that grows tall enough can enter colder regions of the atmosphere, where the droplets begin to freeze. Ice crystals form. Supercooled water droplets cling to them. Collisions happen gently, silently, building particles larger and heavier. Inside the cloud, invisible winds are moving in different directions. Updrafts lift moisture upward. Downdrafts bring cooled air back down. The cloud becomes a living system, not chaotic, but active, like a slow orchestra of air currents playing in the dark. And this is how towering thunderheads begin to form. These are called cumulonimbus clouds, wide at the base and reaching high into the sky, sometimes stretching all the way to the boundary between the lower atmosphere and the stratosphere. That boundary is called the tropopause, a kind of ceiling for most weather. When a cumulonimbus reaches this high, its top often spreads outward, flattening into a shape like an anvil. It's as if the cloud has risen until it can rise no more, and so it gently spills outward instead. And in that shape, towering and vast, we find one of nature's most dramatic sky sculptures, a storm cloud, not because it is angry, not because it is violent, but because it is full of rising air, full of condensed moisture, full of energy gathered slowly from warmth below and cold above. So when you see a cloud beginning to stretch upward, when you notice a bright cumulus turning into something taller, something darker, something more powerful, you are watching the atmosphere at work. You are watching warm air rise, moisture condense, instability build, and you are witnessing an ordinary cloud becoming something grand, something deep, something storm-born, a quiet monument of weather, slowly sculpted by the sky. Storm clouds appear dark because they block sunlight, but the science is more nuanced. So now, as we continue drifting through the calm layers of the atmosphere, let's gently explore the way storm clouds hold light. You may have noticed it before, a bright day full of open blue sky. And then, somewhere in the distance, a cloud begins to gather. It rises higher than the others. Its base becomes wide and heavy, and beneath it, the world begins to dim, as if someone has softly lowered the brightness of the afternoon. The cloud looks darker, almost grey, sometimes nearly black. And while it's true that storm clouds block sunlight, the real story is quieter and more detailed, a gentle dance between light and water. To understand this, we can begin with the nature of sunlight itself. Sunlight is made of many wavelengths of light traveling together, like a choir of colors moving through space. When sunlight reaches Earth's atmosphere, it interacts with air molecules, dust, and water droplets. Some of it continues downward. Some of it is scattered in different directions. This scattering is why the sky appears blue, because shorter blue wavelengths scatter more easily through the air. It's a soft effect, happening constantly above us, painting the daytime sky. But clouds are different. Clouds are made of countless tiny droplets of water, and sometimes ice crystals too. These droplets are far larger than the molecules of air, and so they scatter sunlight differently. In small, thin clouds, light passes through more easily. The droplets scatter the sunlight in many directions, but not enough to stop it from traveling. This is why some clouds appear bright and white. The sunlight is bouncing around inside them, reflecting outward, creating that glowing softness we often associate with fair weather. But storm clouds are thicker. They contain far more water. Their droplets are denser, packed closely together. Their vertical depth can be immense, sometimes stretching miles from base to top. And as sunlight enters a thick cloud, it must travel through layer after layer of water droplets. Each droplet scatters the light again and again. The deeper the cloud, the more chances the light has to be redirected, reflected upward, or absorbed within the cloud's interior. The sunlight becomes trapped in a maze of mist and water, and only a little of it escapes downward. This is one reason storm clouds appear dark from below. We are standing in the shadow of something massive, a floating structure made of water and air, thick enough to interrupt the normal path of daylight. But there is another detail too, one that makes storm clouds even darker. The base of a storm cloud often holds the heaviest concentration of water droplets. Rain may be forming. Droplets may be merging into larger drops. The air beneath may be filled with moisture, haze, and falling precipitation. Larger droplets absorb more light than smaller ones. So as storm clouds grow mature, their bases become less reflective and more light-hungry. They don't scatter sunlight outward in the same bright way. Instead, they keep it. And so, the underside darkens. Sometimes, the contrast is especially striking because of what surrounds the storm cloud. If the sky nearby is still bright, filled with scattered sunlight, the storm cloud looks even darker by comparison. The eye sees the difference, the dramatic shading, and interprets it as heaviness. It is not a sign of danger, necessarily, but a sign of thickness, of depth, of moisture. It is the shadow of water suspended above you. We can also think about the direction of the sun. When the sun is lower in the sky, such as in late afternoon or early evening, the light has to travel through more atmosphere before it reaches the cloud. That light becomes warmer, softer, and weaker. And if a towering storm cloud rises into that fading light, it may appear even more dark and dramatic, like a silhouette against the last golden glow. There is something cinematic about it. The cloud becomes a curtain, a soft dimming of the world, a slow shift from bright to muted. And when rain begins to fall beneath it, the falling droplets scatter, light too, creating grey streaks and veils that deepen the shadow even further. The cloud no longer looks like a simple puff in the sky. It becomes a wide, layered structure, full of moving water and hidden light. So storm clouds appear dark, not because they are filled with darkness, but because they are filled with water, because they are thick enough to scatter and absorb sunlight before it reaches the ground, because light enters them and doesn't easily return. And as you imagine that gentle fading of daylight, that quiet shadow spreading across the land, you can almost feel the atmosphere settling, not with urgency, not with fear, but with softness, a reminder that even light must rest sometimes, and that the sky too knows how to dim itself into calm. The more water a cloud contains, the darker it appears. And now, as we continue drifting through this quiet sky story, we arrive at something simple, yet strangely beautiful: darkness. In a cloud is often not about colour at all. It is about weight. It is about fullness. It is about how much water the sky is holding, and how thickly that water is gathered into one slow-moving place. When a cloud is thin, it lets sunlight wander through it. Light slips between droplets, bouncing softly, scattering outward, leaving the cloud looking pale and bright. The cloud becomes a gentle lantern in the sky, glowing from within. But when a cloud begins to gather more moisture, it starts to change. The more water a cloud contains, the darker it appears. This is one of the simplest truths of storm cloud science, and also one of the most quietly poetic. Because when the sky fills itself with water, it also fills itself with shadow. Let's gently examine how increasing water content thickens the cloud, preventing light from passing through, and casting the skies in moody, sleep-slowed greys. Clouds are made of countless tiny droplets. Each one is so small that it can float, suspended in air, held up by gentle turbulence and rising currents. A single droplet is almost invisible, like a speck of mist. But a cloud is not made of a few droplets. A cloud is made of billions, trillions, a whole drifting population of water, gathered together into a soft mass that the wind can shape like clay. In a fair weather cumulus cloud, the droplets are spread out more loosely. There is space between them. Sunlight enters, scatters, and escapes again. The cloud appears white because it reflects nearly all wavelengths of visible light in every direction. But as a cloud grows, the droplets multiply. Moisture continues condensing. The air inside becomes more saturated, more crowded with liquid. And suddenly, sunlight has a harder journey. Instead of passing through quickly, it must push through layer after layer of droplets. Each droplet scatters the light, bending it, redirecting it. Some of that light is reflected back upward toward the sky. Some is scattered sideways, and less of it reaches the bottom. So, from beneath the cloud, we see less light, and what we see instead is the shadowed underside, the part of the cloud where sunlight struggles to reach. This is what we call cloud optical thickness, a gentle scientific phrase that simply means how hard it is for light to travel through the cloud. A thicker cloud is darker because it blocks more sunlight, and a thicker cloud is thicker because it holds more water. The density of droplets matters too. When droplets are packed closely together, light can't slip between them. It bounces repeatedly, like a traveller lost in a foggy forest. The deeper it goes, the more it is scattered away from its original path. And so, the cloud becomes dim, not because it is filled with darkness, but because it is filled with substance. Water is transparent when it is alone, but when water is gathered into billions of droplets, suspended together in layers, it becomes something else entirely. It becomes a veil, a curtain, a soft, drifting ceiling, and this veil can grow heavy. As storm clouds mature, their droplets often become larger. Tiny droplets collide and merge into bigger ones, a slow process called coalescence. Larger droplets fall more easily, and this is one step toward rain. But larger droplets also scatter and absorb light differently. They do not reflect sunlight as efficiently as tiny droplets. Instead, they can absorb more light, especially when the cloud becomes deep and thick. This is why the underside of a storm cloud can appear almost charcoal grey. It is the shadow of water, layered in such depth that sunlight cannot fully penetrate. Sometimes, the cloud is so dense that even during midday, it feels like evening beneath it. The land cools, the colours fade, the world becomes quiet, as if the atmosphere itself has decided to dim the lights. And this is the birth of cloud darkness. Not a sudden darkness, not a dramatic one, but a slow thickening, a gradual filling, a sky that becomes saturated with water until light can no longer pass through easily. So, when you look up at a storm cloud and see its heavy grey underside, you are witnessing the invisible math of moisture, the quiet accumulation of droplets, the thickening of the sky, and the gentle truth that when water gathers in enough abundance, it naturally creates shadow, a darkness born not of threat, but of depth. As we relax deeper, we follow a cloud's soft evolution from fluffy white to heavy grey. And as we continue our slow journey through the atmosphere, we can imagine watching a single cloud over time, the way it shifts and changes as though it's breathing. At first, it appears almost innocent, a bright puff against the blue. Its edges are crisp, glowing in sunlight. Its body is white because it is still thin enough for light to bounce through it freely. It looks like something light enough to drift forever, but clouds are always becoming. Even when they seem still, they are transforming. Water vapor is rising, air is cooling, droplets are forming, and slowly the cloud begins its gentle evolution. We'll float along this dreamy transformation and watch the sunlight fade as the cloud thickens and grows. At the beginning of this journey, a cloud's whiteness is a sign of openness. Light enters easily. It scatters off tiny droplets and escapes again. The cloud becomes bright because it is sharing light, reflecting it outward like a soft mirror. But then, the cloud grows. More warm air rises into it from below, carrying invisible moisture. As that air cools, more vapor condenses into droplets. The cloud expands upward and outward, slowly building itself into a larger shape. The top becomes taller, the sides billow, the underside flattens, and with every new droplet that forms, the cloud becomes a little thicker, a little deeper, a little more full. At first, the change is subtle. The cloud may still look mostly white, but small areas begin to dim. The bottom becomes slightly less bright. The light seems less evenly spread. This is because sunlight is now traveling through more cloud material before it can reach the base. The deeper the cloud becomes, the longer the light must wander through it, and the more it wanders, the more it gets scattered away. In a thin cloud, light can pass through in seconds, bouncing gently and exiting without much resistance. But in a thicker cloud, light is scattered again and again. It may reflect upward, never reaching the bottom at all. And so, the underside begins to turn grey. Grey is not really a colour inside the cloud. It is the absence of light reaching your eyes. A grey cloud is simply a cloud that is no longer letting sunlight travel through it easily. As the cloud continues growing, its droplets may also begin to merge. They become slightly larger, heavier, and more capable of forming drizzle or rain. This adds to the deepening tone, because larger droplets can absorb more light and scatter it differently. So the cloud becomes darker, but not in a sudden way. It deepens like twilight. It shifts like a room when the curtains are drawn. It moves from bright white to pale grey to a heavier, richer shade. And sometimes, as the cloud thickens further, the contrast becomes striking. The top may still catch sunlight, glowing brilliantly, while the underside turns dark and moody. From below, it looks like two different worlds stacked together, light above, shadow below. This is especially common in growing storm clouds, where the upper portions rise into brighter air, while the base becomes packed with moisture and thick layers of droplets. As we watch this slow transformation, we can almost imagine the cloud as a living thing, not alive in the way animals are alive, but alive in the way weather is alive. A system, a cycle, a gathering, a slow conversation between warmth and cold. And the deepening from white to grey is simply part of that conversation. It is the cloud becoming more mature, more saturated, more layered, more capable of holding rain. So, when you see a cloud begin to shift color from bright to muted, from soft white to sleepy grey, you are not just watching a change in appearance. You are watching moisture accumulate. You are watching sunlight struggle. You are watching thickness build, layer by layer, droplet by droplet. And in that gradual deepening, the sky becomes quieter. The world below becomes calmer. The brightness softens and everything slows, as if the atmosphere is preparing the scene for a gentle, drifting evening. A cloud, once feather-light, becomes a heavier shape, not harsh, not threatening, just full. And in its fullness, it carries the soft grey hush that stormy skies are known for. A peaceful dimming of daylight, one slow breath at a time. What makes some clouds seem darker from below, as we rest beneath the sky, letting our thoughts soften and our breathing slow. This is a gentle question to hold in the mind, because sometimes a cloud doesn't just look grey. Sometimes it looks almost ink dark, like a heavy ceiling hanging low over the world. And yet, if you were able to rise above it, to look down from an airplane window, the very same cloud might appear bright and white, glowing softly in the sunlight. So, why does it look so different from below? Tonight, we'll explore this quietly, like a slow walk through evening air. Not with urgency, not with sharp explanations, but with calm understanding, unfolding one layer at a time. What makes some clouds seem darker from below is not only what the cloud is made of, but where you are standing in relation to the sun, the cloud, and the light itself. As we lie beneath the sky, we'll explore how sunlight angles, viewer position, and thickness above combine to paint the ceiling of the world in dramatic hues. Let's begin with the sun. The sun is always shining, even when we can't see it. Its light travels in straight lines, spilling across the atmosphere and striking everything it meets. But the angle of that light changes throughout the day. When the sun is high overhead, sunlight comes down more directly. It has a shorter path through the atmosphere. The light is strong and bright, and clouds are often illuminated from above with intensity. Even thick clouds may look lighter because the sun is pouring into them from a near vertical angle. But when the sun is lower in the sky, during early morning or late afternoon, the sunlight arrives at a slant. It must travel through more atmosphere, scattering and weakening along the way. It becomes softer, warmer, more golden. And this angled light changes how clouds appear. A thick cloud lit from the side may glow brilliantly on one edge, while casting deep shadow across its base. The contrast becomes sharper. The underside becomes darker. The cloud looks more dramatic, more sculpted, like a mountain range carved out of shadow. Now, let's think about your position as the viewer. When you look at a cloud from below, you are looking at its thickest, most moisture-filled region. Many clouds, especially storm clouds, are densest at the bottom. This is where droplets gather, where precipitation begins to form, and where the cloud's interior is often hidden from light. The top of the cloud may be bright and sunlit, but you cannot see that part easily from the ground. Instead, your eyes meet the underside, the shaded base, the part where light has already been scattered and absorbed above. In a way, you are looking at the cloud's shadowed belly, and the cloud is looking back at you, quiet and heavy, like a dim ceiling. This effect becomes even stronger when the cloud is thick. A thin cloud allows light to pass through. It may still cast a shadow, but it will appear soft and pale. But a thick cloud acts like a barrier. Sunlight enters from above and gets scattered repeatedly inside, like a beam of light wandering through fog. Much of that light never makes it through to the bottom. Instead, it escapes upward or sideways, leaving the underside with very little illumination. And when there is little light, the cloud appears dark. Sometimes, the darkness is intensified by what is beneath the cloud. Over land, forests and cities absorb sunlight and reflect less light upward. Over water, the reflection may be different, adding subtle changes in tone. Even the presence of rain can deepen the effect. When rain begins to fall beneath a cloud, it creates a curtain of droplets that scatter light away from your eyes. This veil of precipitation can make the base appear darker still, as if the cloud has grown heavier and closer. And then there is one more quiet factor: contrast. Our eyes are always comparing brightness. If a storm cloud forms next to a bright patch of sky, the difference can make the cloud look much darker than it truly is. The bright sky becomes a backdrop, and the cloud becomes a silhouette. The same cloud on an already grey day may appear less dramatic, simply because the surrounding light is muted. So the darkness of a cloud is not only about the cloud itself, it is also about the angle of sunlight, the direction of your gaze, the thickness of water above, and the way your eyes interpret shadow. It is a painting made of physics, a quiet geometry of light and moisture. And as you imagine yourself lying beneath such a sky, watching the slow movement of clouds overhead, you might notice how peaceful it can feel when the light dims. Not frightening, not intense, just soft, like the world has lowered its voice. A storm cloud becomes a shadow, not because it is cruel, but because it is full, and because light must travel a longer, more complicated path to reach you. And in that deep shadow, the sky becomes a calm ceiling of grey, gently inviting the earth below to slow down and rest. Let's journey gently into the anatomy of a thunderstorm cloud. As we continue drifting through this nighttime documentary of weather, we arrive at one of the most famous cloud shapes in the sky. The kind that rises higher than all the others. The kind that looks like it belongs in a painting, or in the background of a distant horizon. The cumulonimbus. Even its name sounds like something ancient and grand, like a mountain range made of air. Towering and vast, cumulonimbus clouds rise like castles in the sky, their bases often in deep shadow, their tops catching golden light. And it's true, if you've ever watched one from far away, you may have noticed how it seems to build itself upward with patience. It begins as a simple cumulus cloud, bright and puffy, floating lazily in the warmth of the day. But beneath that calm exterior, the atmosphere is quietly preparing something larger. The story of a cumulonimbus begins with warm air rising. When the ground is warmed by the sun, pockets of air near the surface become buoyant. They lift upward, carrying moisture with them. This is convection, the gentle engine that powers many of the sky's most dramatic shapes. As that air rises, it cools, and as it cools, the invisible water vapor inside begins to condense into droplets. At first, the cloud remains small, but if the atmosphere is unstable, meaning the air above is cooler and encourages rising motion, the cloud continues to grow. It grows upward like a slow tower. Updrafts feed it constantly, pulling more and more moist air into its core. The cloud becomes taller, deeper, heavier. Its bright edges remain sunlit, but its interior begins to darken with density. And as it rises higher, it enters colder regions of the sky. Here, droplets can freeze. Ice crystals form. Supercooled water droplets cling to those crystals, building them larger. Tiny particles collide gently in the turbulent air, creating snow-like clusters and soft pellets of ice. Some will melt into rain as they fall. Some may remain frozen, depending on the temperature layers below. Inside the cumulonimbus, invisible motion is everywhere. Strong updrafts lift droplets high into the cloud. Downdrafts bring cooled air downward. This circulation creates a living structure, a slow atmospheric machine built from warmth and water. But from the ground, it simply looks like a giant. Its base is usually wide and dark because it contains the thickest concentration of droplets and precipitation. Sunlight struggles to reach through that deep moisture, so the underside becomes shadowed, a dim grey floor hanging over the land. Above that base, the cloud rises in vertical columns. The sides may be textured and billowing, like stone walls in a castle. The edges may glow where sunlight strikes them. And then, at the top, something beautiful often happens. The cumulonimbus reaches the tropopause, the boundary where the lower atmosphere meets the stratosphere. Above this level, the air becomes more stable, and rising motion is restricted. The cloud can no longer climb. So, instead, it spreads outward. This creates the famous anvil shape, a wide, flattened top like a giant umbrella of ice crystals, fanning out across the sky. In late-day sunlight, this anvil can shine gold, peach, or pale silver, even while the base remains dark and shadowed. It is one of the most striking contrasts in all of meteorology. Light above, shadow below, a cloud that holds two worlds at once. And because cumulonimbus clouds are so tall, they can contain multiple phases of water, liquid droplets, ice crystals, and even hail. They are like floating laboratories of physics, where temperature, moisture, and motion are constantly shaping one another. But despite their power, they are also deeply natural. They are not monsters. They are not angry. They are simply the atmosphere expressing energy, releasing heat upward, redistributing moisture, balancing itself through motion. A cumulonimbus is the sky's way of breathing out what it has gathered, and from a distance they can look peaceful, slowly drifting castles, soft grey mountains, silent towers that rise and spread into the upper air. So, when you see one forming on the horizon, you are witnessing one of Earth's grandest weather sculptures, built from warm air rising, moisture condensing, and the invisible architecture of the atmosphere. A giant of the sky, calmly towering, quietly unfolding, and catching the last golden light as evening approaches. We'll float through the perception of weight in clouds. As we rest beneath the wide ceiling of the sky, it can be easy to forget that clouds are not solid things. They do not have bones or stone. They do not hang from anything. They are made of air and water and invisible motion. And yet, some clouds feel light, like drifting feathers, while others feel heavy, like the sky itself is pressing down. A storm cloud can appear as though it has weight, not just physical weight, but emotional weight, a mood, a presence, a slow gravity in the air. Though they're made of vapor and mist, storm clouds feel heavy in mood and presence. We'll softly explore the sensory science of this illusion, because what we experience when we look at a storm cloud is not only meteorology, it is perception. It is the way the brain interprets shape, color, shadow, and scale. It is the way the body responds to dimming light and changing air. It is the quiet psychology of the sky. Let's begin with something simple: darkness. A cloud that is bright and white feels light because it reflects sunlight. It seems airy, open, harmless. Its edges glow, and its underside still holds brightness. But a storm cloud is often darker. Its base may be deep grey or charcoal, and darkness, to the human mind, is often associated with weight. We naturally interpret darker objects as heavier, denser, and more solid. It is the same reason a dark stone feels heavier than a pale one, even if they are the same size. Darkness suggests mass, and storm clouds are full of it. Not darkness itself, but water. Their droplets are packed closely together, and their thickness blocks sunlight, creating shadow. The base becomes dim, and that dimness gives the illusion that the cloud is heavy enough to sink lower. But there is more than colour. There is also scale. Storm clouds are often enormous. A cumulonimbus cloud can rise miles into the atmosphere, stretching upward like a tower. But from the ground, we cannot easily measure that height. Instead, we feel it. We sense it through the way it dominates the horizon. We see it occupying the sky like a mountain, and the mind interprets large objects as heavy. Even if the object is made of mist, its size suggests power and mass. The cloud becomes a presence, a structure, a floating continent. And then there is the shape. Fair weather clouds tend to have rounded tops and soft edges. They appear playful, like slow-moving foam. But storm clouds often have flatter bases, sharp outlines, and towering vertical walls. Their undersides can appear smooth and low, like a lid placed over the world. This shape feels heavier because it resembles something solid, like a ceiling, like a stone slab. And the brain is always searching for familiar patterns. So it interprets that flat, dark base as weight. But the illusion of heaviness is not only visual, it is also physical. Before a storm, the air often changes. Humidity rises. The atmosphere may feel thick, warm, and still. Wind may pause for a while, as if the world is holding its breath. This can create a sensation of pressure, a quiet heaviness in the air itself. Even though the actual air pressure may not always be dramatically different, our bodies notice subtle shifts. Moist air can feel denser against the skin. The scent of soil, plants, and distant rain becomes stronger. Sometimes the temperature drops slightly as the cloud blocks sunlight. And when the light fades, the world becomes quieter. Birds may settle, colours dull, shadows deepen. The entire landscape slows down. And this change in atmosphere affects our emotions. Humans are deeply sensitive to light. When brightness decreases, the nervous system often relaxes. The world feels more enclosed, more intimate, as if we've moved indoors. This can feel comforting, but it can also feel weighty, like the sky has drawn a blanket over the earth. Storm clouds also often produce visible curtains of rain beneath them. These streaks create the impression of something falling, something pulling downward. Even if the rain hasn't reached you yet, seeing those grey veils makes the cloud feel heavy, as though it is spilling over with water. And in a way, it is, because storm clouds do contain tremendous amounts of water. Not enough to fall as a lake all at once, but enough to feed rivers, wash streets, and soak fields. The water is spread out in droplets and ice crystals, suspended by rising air. But it is real, so perhaps the heaviness we sense is not entirely an illusion. It is the truth of moisture gathering, the truth of density, the truth of a sky holding weight in a floating form. And yet, even as we acknowledge the science, we can also appreciate the feeling, the way a storm cloud makes the world seem slower, the way it dims the day into a softer grey, the way it feels like the sky has leaned closer, lowering its voice. A storm cloud is still just air and water, but to the senses, it becomes something heavier, a mood you can see, a presence you can feel, a gentle reminder that even the sky can carry weight, quietly, beautifully, and without haste. Cloud brightness is measured by a property called albedo, and now, as we drift deeper into the quiet science of light and shadow, we arrive at a word that sounds soft and smooth, like something whispered through fog: albedo. It is not a word that needs to feel technical. In truth, it describes something very simple: how much light a surface reflects. High albedo clouds reflect more light, low albedo ones absorb it. And when we speak of clouds, albedo becomes a kind of gentle measurement of brightness, a way to understand why some clouds gleam white like snow, while others deepen into grey. To imagine albedo, you might picture a landscape covered in fresh snow. Snow reflects a great deal of sunlight. That is why it looks so bright, sometimes almost blinding. It does not hold light, it sends it back. Snow has a high albedo. Now imagine the same landscape, but covered in dark soil or wet asphalt. Those surfaces absorb more sunlight. They do not reflect much. They keep the energy warming up under the sun. Those surfaces have a low albedo. Clouds behave in a similar way. We'll drift through this concept as if watching shadows move through snow. A thin, fair weather cloud is often bright because it reflects sunlight efficiently. The droplets inside it are small and numerous, and they scatter light in all directions. Much of that light is reflected back upward into space. This is why clouds play such an important role in Earth's climate. Bright clouds can cool the planet by reflecting sunlight away before it reaches the ground. In a way, they are like floating mirrors. But as a cloud grows thicker, its albedo can change. At first, a thicker cloud might reflect even more sunlight, becoming brilliantly white when viewed from above. This is why the tops of large clouds often appear dazzling from airplanes or satellites. The upper surface is catching sunlight directly, scattering it back like a wide sheet of glowing cotton. From above, the cloud can look almost radiant, but from below, the story is different. A thick cloud may still have high albedo on top, but its underside can appear dark because very little light makes it through. The cloud is reflecting sunlight upward, not letting it pass downward. So the albedo depends on perspective. From space, a storm cloud can be bright. From the ground, it can feel like twilight. This is one of the quiet paradoxes of clouds. They can be both brilliant and shadowed at the same time. Cloud composition also matters. Clouds made mostly of small water droplets tend to reflect more light. But clouds containing larger droplets, heavy rain, or mixed ice crystals can absorb more light and scatter it less evenly. This can lower the albedo in certain parts of the cloud, deepening its grey tones. A cloud is not a single uniform object. It has layers and textures. Some parts are thin and reflective. Other parts are dense and absorbing. So, albedo is not fixed. It shifts as the cloud changes. It shifts as droplets grow. It shifts as sunlight angles across the sky. And it shifts with time, like the slow movement of shadows across a snowy field. In the early morning, when sunlight is low and warm, clouds may appear softer in colour. Their brightness becomes golden, not white. Their reflected light is tinted by the atmosphere's long path of scattering. In midday, the same clouds may appear crisp and bright, their albedo shining clearly, and in evening they may turn peach, lavender, or deep grey as the light fades. This is not because the cloud is changing colour, but because the light itself is changing. So, when meteorologists talk about albedo, they are speaking about reflection, but also about energy. A reflective cloud sends sunlight away, keeping the surface cooler. A less reflective cloud allows more sunlight to reach the ground, warming it. In this way, clouds are not just beautiful shapes. They are active participants in the balance of the planet. They decide, in their quiet, drifting way, how much warmth the Earth receives. And this can be imagined gently, like watching sunlight fall on snow and noticing where the snow gleams and where the shadows gather. Clouds, too, have their bright places and their shadowed places, their high albedo moments and their low albedo hush. And as we lie beneath them, watching the sky shift from light to grey, we are witnessing reflection in motion, a slow atmospheric art, a floating mirror turning gradually into velvet, a soft reminder that even light can be measured, and even shadows have science behind them, quietly unfolding above us as the world below drifts towards sleep. Beneath a storm, rising air feeds the cloud from below. As we continue drifting through the quiet architecture of the sky, we arrive at something you cannot see, and yet it is always there. Motion, not hurried motion, not chaotic motion, but steady, invisible lifting. Storm clouds do not simply appear fully formed. They are built, slowly, from below, fed by rising air that carries warmth and moisture upward like a gentle offering. These rising currents are called updrafts, and though they are made only of air, they behave like invisible elevators, lifting water vapor skyward, story by story, into the growing tower above. Let's ride one, slowly and calmly, as the cloud darkens around us. Imagine standing on warm ground in the afternoon. The sun has been shining for hours, and the surface has absorbed its energy. Roads, fields, rooftops, all quietly warmed. The air touching that surface warms too. Warm air is lighter than cool air. Its molecules move a little faster, spread a little farther apart, and because it is lighter, it begins to rise. Not all at once, not in a rush, just a slow upward drift. Now imagine yourself inside that rising pocket of air. There is no sensation of speed, no wind rushing past, just a steady lifting, as though the atmosphere itself has decided to carry you upward. As this air rises, something gentle but important begins to happen. The pressure around you decreases with height, and when air rises into lower pressure, it expands. As it expands, it cools. This cooling is gradual and natural, a soft transition from warm to cooler air. And as the air cools, it reaches a point where it can no longer hold all the invisible water vapor it carries. The vapor begins to condense. Tiny droplets form. You are now inside a cloud. At first, it is bright and white. Sunlight filters through easily. The droplets are small, scattered like fine mist. You continue rising, carried by the updraft that feeds the cloud from below. Below you, more warm air rises, joining the column. The cloud thickens. The updraft strengthens as long as the surrounding atmosphere remains unstable, meaning the air around you is cooler than the air inside your rising column. This difference keeps you buoyant, keeps you climbing, and as you rise, the cloud builds upward with you. This is how vertical towers form. Updrafts transport moisture skyward, building vertical towers of water droplets and, eventually, ice crystals. Each rising column adds height to the cloud. Each layer becomes part of a growing structure. From the ground, this appears as a cloud stretching taller and taller, its sides billowing like slow-motion waves frozen in place. Inside, it is a quiet engine. Updrafts can be surprisingly strong in mature storms, but we are imagining the gentle version, the calm ascent, the slow elevator ride through soft mist. As you continue upward, the cloud begins to darken beneath you, not because it is threatening, but because it is thickening. More droplets gather. Light struggles to pass all the way through to the base. The underside becomes shaded, a deepening grey. Above you, however, the cloud may still be bright, because sunlight is still entering from the top, illuminating the upper layers even as the lower ones fall into shadow. This is the duality of a storm cloud: light above, dimness below, and between them, constant upward motion. Eventually, as you rise higher, temperatures drop further. Some droplets begin to freeze into ice crystals. The cloud becomes more complex, part liquid, part ice, its structure shaped by temperature and motion. And still, the updraft carries you, until, at last, the air around you becomes too stable to allow further ascent. The invisible elevator slows, the rising motion weakens, and the cloud begins to spread outward instead of upward. But beneath it all, the process continues. Warm air rises, moisture condenses, the cloud is fed from below, layer upon layer. So, when you look at a storm cloud towering overhead, you are seeing the result of countless invisible elevators lifting water skyward. A vertical journey powered by warmth, a quiet architecture built from rising air. And though we cannot see the updrafts themselves, we can see their work in the height of the cloud, in the darkness gathering at its base, in the towering walls reaching for the upper sky. The storm is not falling from above, it is rising from below, built gently, steadily, by air that simply wanted to rise. Why do storm clouds look dark below, but shine above? As we continue our ascent through this soft meteorological landscape, we now rise higher, above the dim underside, above the heavy grey base, into the upper reaches of the storm cloud. And here, the world changes. Below, the ground may be shaded, the air may feel cooler, the sky may seem heavy, but above, sunlight still dances. We rise into the upper reaches, where sunlight still glows across icy anvils, even as the ground below grows dim. This contrast is one of the most beautiful illusions in the sky. From the surface, a storm cloud can look dark and imposing. Its base blocks sunlight. Its thickness absorbs and scatters light before it can reach the earth. But the sun has not disappeared. It is still shining, and the top of the cloud is still bathed in that light. To understand this, we return to perspective. When you stand beneath a storm cloud, you are looking at the bottom, the thickest, densest region, often filled with rain droplets and deep moisture. Light entering from above has already been scattered multiple times before reaching this lower layer. Much of it never arrives, so the underside appears dark. But if you were to rise above the cloud into an airplane, perhaps you would see something entirely different. The cloud's top is brilliant because it is the first surface to receive direct sunlight. The upper portions of a cumulonimbus cloud can reach heights of 30,000 to 50,000 feet or more. At these altitudes, the air is thinner, colder, and often clearer. The cloud's summit spreads outward when it reaches the stable boundary of the tropopause, forming the familiar anvil shape. And this anvil is often composed largely of ice crystals. Ice crystals scatter sunlight beautifully. They reflect and refract light in delicate ways, sometimes producing halos, sundogs, or shimmering brightness. Even without these optical effects, the upper cloud surface can gleam white or golden in direct sunlight, especially during late afternoon. When the sun is low, its light becomes warmer, richer in oranges and golds. That angled light can strike the towering top of a storm cloud, igniting it in soft amber hues. Meanwhile, the ground below may already be in shadow. The base of the cloud blocks the direct sunlight from reaching the land. So, the earth grows dim while the cloud's summit glows. It is as though the cloud exists in two different times of day at once. Daylight above, twilight below. This happens because light travels in straight lines. The sun's rays strike the highest surfaces first. Anything below that line of sight, like the ground beneath the cloud, remains shaded. And because storm clouds are so tall, this separation can be dramatic. In some cases, rain may be falling beneath the cloud while the top shines brightly overhead. The rain curtains can even catch stray beams of light, creating soft gradients of grey and silver. It is a layered world. Shadow, rain, light, ice, all stacked vertically within the same structure. And this vertical layering reminds us that weather is three-dimensional. We often think of the sky as a flat ceiling, but it is more like a deep ocean above us, full of levels and currents and shifting light. The darkness below is not the whole story. It is simply one layer. Above it, sunlight continues its quiet work, illuminating ice crystals, warming the cloud's upper edges, painting the anvil in luminous tones. So when you see a storm cloud glowing at the top while its base remains dark, you are witnessing geometry in motion. The angle of the sun, the height of the cloud, the thickness of moisture, all combining to create contrast. And there is something deeply calming about this image. The idea that even when things look dim from where you stand, light may still be touching the highest parts, that above the shadow, brightness remains. A storm cloud can hold both darkness and light at once. And as we drift gently downward again, returning to the shaded ground below, we carry with us the knowledge that the sun never truly left. It simply illuminated a different layer, and the cloud, vast and towering, quietly held both worlds at the same time. As droplets gather, the cloud thickens, and now, as we continue our gentle descent through the layered architecture of a storm, we begin to notice something changing in the air around us. The droplets are no longer as tiny as they once were. Higher up, they were fine and mist-like, suspended easily by rising currents. But here, deeper within the cloud, they begin to merge. They collide softly, cling together, and grow heavier. This quiet process, called coalescence, is one of the ways rain begins its journey. And as these droplets gather and grow, the cloud itself changes. It becomes thicker, denser, more layered. Will drift downward through layers of growing rain, each droplet scattering and absorbing light, dimming the sky and deepening the shadows. Imagine floating slowly through this interior world of water. At first, light still filters through in pale streaks. It is scattered gently by countless small droplets, bouncing from one to another, like whispers, moving through a crowd. But as the droplets grow larger, their relationship with light changes. Small droplets scatter light very efficiently. They send it in many directions, often making thin clouds appear bright and white. But larger droplets, those heavy enough to fall as rain, scatter light differently. They tend to absorb more of it and allow less to pass cleanly through. So, as rain begins to form, less sunlight makes it through the cloud's lower layers. Each droplet becomes a tiny lens, and also a tiny obstacle. Light enters the droplet and bends slightly. Some of it exits in new directions. Some of it is reflected internally. Some of it is absorbed as heat. And when billions of droplets are doing this all at once, the effect becomes noticeable. The sky below grows dimmer. This is why the arrival of rain often feels like the arrival of evening, even in the middle of the day. The falling droplets create a curtain between the sun and the ground. This curtain scatters light sideways and upward, preventing much of it from reaching the earth directly. The world becomes softer. Edges blur, colors mute, even sounds change. Rain absorbs and diffuses sound waves as well, creating that familiar hush, the quiet blanket of rainfall that makes everything feel enclosed and still. But the dimming of light is especially powerful. As we drift lower, we pass through thicker bands of precipitation. The droplets here are larger and more numerous. They fall in steady lines, pulled gently downward by gravity, even as rising air currents try to lift them again. This tug of war inside the cloud shapes its interior texture. But from below, what we notice most is the shadow. Rain deepens the darkness because it adds both density and motion to the cloud's underside. The falling droplets scatter sunlight before it reaches the ground. They also make the base appear more opaque, more solid. In heavy rainfall, the curtain of water can be so thick that distant buildings or hills disappear into grey. It is not the absence of light, but the constant redirection of it. Light is still present. It is simply being scattered in too many directions to travel clearly to your eyes. Sometimes, if sunlight breaks through from the side, rain can shimmer. You might glimpse faint brightness within the falling sheets, even hints of colour if conditions are just right. But often, rain carries with it a soft dimness, a deepening, a lowering of the sky's brightness into restful grey. And yet, even in this dimness, there is something soothing. Rain is the release of what the cloud has been holding. All that gathered moisture, lifted by updrafts, condensed in cool air, thickened into droplets, now returns to the earth. The darkening sky is part of that process. The cloud must grow dense before it can let go. When rain begins and the sky grows darker, you are witnessing the natural result of water gathering and light interacting with it. Droplet by droplet, layer by layer, each one scattering and absorbing sunlight, each one contributing to the gentle shadow that spreads across the land. It is not a harsh darkness. It is a filtered one, a softened ceiling, a quiet dimming created by countless tiny spheres of water falling in patient descent. And as the rain continues, the world below becomes quieter still, wrapped in shadow, bathed in soft grey light, and held beneath a sky that has grown heavy enough to let go. High in the heart of a thunderhead, ice crystals swirl. And now, as we rise again through the towering structure of a storm cloud, we enter a colder realm. Far above the rain-filled lower layers, above the thick grey base, the air becomes sharply cooler. Temperatures drop well below freezing, and yet the cloud continues to exist because water in the atmosphere can take many forms. Here, in the upper reaches of a cumulonimbus cloud, droplets begin to freeze. Some freeze instantly when they collide with tiny particles in the air. Dust, salt, or microscopic fragments that act as nuclei. Others remain liquid even below freezing, in a delicate state known as supercooled water, until they are disturbed, and among them, ice crystals begin to form. We'll float among them and explore how both droplets and ice together help sculpt the storm cloud's dark beauty. Ice crystals are different from liquid droplets. They are often hexagonal in shape, forming delicate plates or columns depending on temperature and humidity. They grow slowly as water vapor deposits directly onto their surfaces, a process called deposition. In the upper cloud, these crystals drift and spin in gentle turbulence. They reflect and refract sunlight in complex ways, sometimes producing brilliant brightness at the cloud's top. But ice also plays a role in the darkness below. As ice crystals grow and collide, they can combine into larger particles, snowflakes, graupel, or hail embryos. Some fall downward into warmer layers, melting into rain. Others remain suspended by strong updrafts. This vertical mixing, ice rising, melting, freezing again, adds to the cloud's internal density. The more material inside the cloud, the thicker it becomes. And thickness affects light. The upper layers may appear bright from above, because ice crystals reflect sunlight efficiently. But deeper within the cloud, where ice and droplets coexist, light becomes scattered in every direction. The mixture of liquid and solid water increases optical complexity. Photons of sunlight entering the cloud are redirected repeatedly, bouncing off ice surfaces, refracting through droplets, absorbed, scattered again. Very little light makes it through intact, so from the ground, the cloud may appear dark. The ice above is still catching sunlight, glowing softly at high altitude. But the dense interior layers, filled with both droplets and frozen particles, block and diffuse that light before it can reach the base. This layered structure gives storm clouds their dramatic appearance. Bright anvil above, shadowed mass below. Ice crystals also influence the texture of the cloud's top. When the cloud reaches the tropopause and spreads outward, the anvil region is composed largely of ice. This creates a smoother, fibrous appearance compared to the billowing lower towers. And in certain angles of light, that icy top can shimmer faintly, even while the earth beneath remains dim. It is a quiet contrast. Cold brilliance above, warm shadow below. Ice is not just decoration in a storm cloud. It is part of the engine. The freezing process releases latent heat, energy that was stored when water evaporated earlier near the ground. This released heat strengthens updrafts, helping the cloud rise even higher. So ice contributes to the storm's vertical growth. It helps the tower climb, and as it does, it adds to the density that deepens the cloud's shadow. Both droplets and ice together sculpt the storm cloud's dark beauty. Liquid water gathers and thickens the lower layers. Ice crystals form and spread in the upper reaches. Between them lies a complex dance of temperature, motion, and light. But from where we stand, far below, it simply looks like a towering grey giant with a luminous crown, a structure holding cold and warmth, shadow and brightness, rain and ice, all at once. And as we drift gently downward again, leaving the icy heights behind, we carry with us the quiet understanding that darkness in a storm cloud is not empty. It is full of droplets, full of crystals, full of processes unfolding in patient balance. A dark beauty sculpted by water in all its forms, quietly swirling high above the sleeping earth. Most dark clouds appear from below. And now, As we continue our gentle exploration of the sky's architecture, we return to the ground. We lie back in the grass of a warm summer field, or perhaps rest beneath a quiet porch roof and lift our gaze upward. Above us stretches the underside of a thunderstorm. From this angle, the cloud feels immense, not just wide, but present. It fills the sky like a vast ceiling, lowered gently over the world. We'll lie beneath the belly of a summer thunderstorm and gaze up at its charcoal base, textured with softness and strength. The base of a storm cloud is where shadow gathers. It is the lowest visible layer of the cumulonimbus, often appearing flat or slightly curved, like the smooth underside of a great stone arch. But unlike stone, it is made entirely of water droplets suspended in air. This is where the cloud is thickest. As warm air rises into the storm from below, it cools and condenses into droplets. These droplets collect and cluster, forming a dense layer. The more moisture that gathers, the less sunlight can pass through from above. So, from where we rest, the base appears dark, charcoal grey, sometimes nearly slate-coloured. But if you look closely, softly, without strain, you may notice that it is not uniform. The underside of a storm cloud is textured. Subtle ripples and folds drift across it. Gentle variations in tone move like slow currents. These textures are shaped by invisible air currents. Rising updrafts feed the cloud, while cooler downdrafts sink through it. These motions create delicate patterns along the base, billows, pouches, and waves of shifting density. It is softness shaped by motion, strength shaped by water, and even though the base appears heavy, it is still only droplets held aloft by air. Each droplet is small, each one floats. Together, they form a layer thick enough to block much of the sunlight above. This thickness is what gives the base its deep tone. Light enters the cloud from above, but it must travel through miles of moisture before it can reach the underside. Along the way, it is scattered repeatedly. Some of it is reflected back upward. Some is absorbed within the cloud's interior. Very little makes it all the way through. So the base becomes a shadow, not a sharp one, but a diffused shadow, soft-edged and enveloping. Sometimes you may notice curtains of rain descending from the base in gentle streaks. These vertical lines add to the sense of weight, like threads hanging from a dark tapestry. Yet, there is calm in this view, because the base of a storm is also a boundary. Above it lies the churning interior of the cloud. Below it lies the world of trees and rooftops and open fields. The base is the meeting point, the threshold where sky and land acknowledge one another. It is also where rain begins its final descent. Droplets that have grown too large for the updrafts to support fall gently from this dark ceiling. Gravity draws them downward in patient arcs, and as they fall, they cool the air beneath the cloud, sometimes spreading outward in soft gusts that ripple across the landscape. But even in this movement, there is rhythm. The base does not rush. It hangs, it breathes, it drifts slowly with the steering winds of the upper atmosphere. If you remain still beneath it, watching without urgency, you may notice how its darkness feels less like threat and more like shelter. The light is dimmed, the world grows quieter, colours deepen. It is as if the sky has drawn a curtain to soften the afternoon, and in that softened light, everything feels closer, more intimate, more enclosed. The base of the storm is often what we remember most, the low, dark ceiling that signals rain and cool air. But it is also simply the densest part of a floating structure built from rising warmth and gathered moisture, a charcoal canopy, a textured belly of water and air, strong in appearance, yet composed entirely of suspended droplets. And as we lie beneath it, gazing upward, we are reminded that even the darkest clouds are made of softness, soft droplets, soft air, soft shadow, held together in a vast, drifting form above our quiet world. We'll explore how light refracts, reflects, and is sometimes trapped inside water droplets, turning bright skies into stormy veils. As we continue drifting through this gentle meteorological meditation, we focus now on something almost magical, though entirely scientific. Light. Not just sunlight as a whole, but individual beams entering a cloud, meeting droplets one by one. Imagine a single ray of sunlight descending from above. It approaches a cloud filled with countless tiny spheres of water. Each droplet is clear, almost invisible on its own, but together they transform the sky. When light encounters a droplet, it does not simply pass through unchanged. It bends. This bending is called refraction. Because water is denser than air, light slows slightly as it enters the droplet. That change in speed causes it to change direction. The beam curves gently inside the sphere of water. Some of that light then exits the droplet, bending again as it returns to air. But not all of it leaves immediately. Some of the light reflects off the inner surface of the droplet, bouncing around inside like a whisper in a glass room. This internal reflection can happen once, or even multiple times before the light finally escapes. In thin clouds, where droplets are small and spaced farther apart, light may pass through with only minor scattering. The cloud appears bright because much of the sunlight is redirected outward toward your eyes. But in thicker clouds, the journey becomes more complicated. The droplet population increases. The spacing decreases. Light that exits one droplet may immediately enter another. It bends again. It reflects again. It scatters sideways or upward. And in this layered maze of water spheres, light becomes diffused. Sometimes it is almost as if the light is trapped, caught in a slow-motion labyrinth of reflections and refractions. Of course, it is not permanently trapped. Eventually, photons escape in some direction. But from the perspective of someone beneath the cloud, very little of that light may escape downward. Instead, it exits upward or sideways, leaving the base dim. This is how bright skies can turn into stormy veils. The cloud itself has not changed color. The droplets are still clear. The sunlight above is still bright. But the repeated bending and bouncing of light within the cloud reduces its direct path to the ground. The sky becomes a diffuser, like frosted glass placed over a lamp. If you have ever watched sunlight pass through a thick shower of rain, you may have noticed how the world looks softened, almost blurred. That is light interacting with droplets in motion. Each droplet acts like a tiny lens. Each one shapes the path of light. In storm clouds, where droplets vary in size, from tiny mist to heavy raindrops, the scattering becomes even more complex. Larger droplets can absorb more light and reflect it differently. Smaller droplets scatter it more evenly. Together, they create gradients of grey, subtle shifts from pale silver to deep slate. And high above, ice crystals add another layer to this optical dance. They refract and reflect light in angular ways, sometimes sending faint glimmers outward, even while the base remains dark. So, when you look up at a storm cloud and see a smooth grey underside, you are witnessing countless acts of refraction and reflection happening at once. millions upon millions of tiny interactions between light and water. Not violent, not chaotic, just constant, gentle physics unfolding in slow motion. And perhaps there is something soothing in knowing this, that the dark veil of a storm cloud is not an absence of light, but the result of light taking a longer, more intricate path, a path shaped by droplets, a path softened by reflection, a path diffused into shadow. The brightness above has not vanished. It has simply been scattered into calm. And as we rest beneath this softened sky, watching the grey tones settle over the landscape, we can imagine each droplet quietly bending light, holding it briefly and releasing it again, turning brilliance into hush, turning glare into glow, turning day into a stormy veil of gentle shadow. A shallow cloud lets more light pass through. A deep one blocks it. And now, as we continue our slow journey through the architecture of storms, we turn our attention to something you cannot measure with your eyes alone. Yet, you can feel it when you look up. Depth. Clouds are not flat shapes painted onto the sky. They are layered structures with thickness, vertical distance from their sunlit tops to their shadowed bases. Some clouds are shallow, others are deep enough to stretch miles upward, and this depth quietly determines how much light can pass through. We'll softly glide through the difference, feeling the weight of moisture gathering. Imagine first a shallow cloud, perhaps a thin layer of stratus drifting lazily across a pale blue afternoon. It hangs low, but it is not tall. Sunlight enters from above and has only a short distance to travel before emerging again from the underside. Along the way, the light is scattered by droplets, but because the cloud is thin, many rays complete their journey. They pass through, softened but still present. From below, the cloud appears light grey, sometimes nearly white. The world beneath it remains illuminated. Now, imagine a different cloud, one that does not simply drift, but builds. Warm air rises steadily from below, carrying moisture upward. The cloud grows vertically, adding layer upon layer of condensed droplets. It stretches higher into cooler air, thickening as it climbs. This is depth increasing, and with depth comes density. The deeper the cloud becomes, the longer the path that sunlight must travel to reach the ground. Each additional layer adds more droplets, more scattering, more opportunities for light to be redirected. In a shallow cloud, light may bounce once or twice before emerging. In a deep cloud, it may bounce dozens of times, scattering sideways, upward, absorbed into warmth, lost in the labyrinth of moisture. By the time it reaches the bottom, if it reaches the bottom at all, it is faint. This is why deep clouds appear darker, not because they are filled with shadow itself, but because their thickness prevents light from completing its journey downward. Let us imagine drifting upward through such a cloud. At the base, it feels dim and grey. As we rise, the light gradually increases. Higher still, near the top, the cloud may glow brilliantly in direct sunlight. The same cloud holds both brightness and shadow, separated by depth. The greater the vertical distance between top and bottom, the greater the difference in light. This depth is especially pronounced in cumulonimbus clouds. These towering giants can extend tens of thousands of feet into the atmosphere. Sunlight entering from above must travel through miles of droplets and ice crystals before it could ever reach the base. Most of it does not. Instead, it is scattered and reflected within the upper and middle layers. So from below, the cloud feels heavy, deep, solid. even though it is made of nothing more than suspended water. There is also something sensory about depth. When we look at a cloud that towers high into the sky, we sense its vertical scale. Our eyes follow its edges upward, tracing its height. This perceived scale adds to the feeling of weight. A deep cloud feels substantial because it occupies more space. It claims more of the sky, and as moisture gathers within it, layer by layer, it becomes optically thick. The scientific term for this is optical depth, a measure of how effectively a medium blocks light. A cloud with high optical depth allows very little direct sunlight to pass through. So, when we speak of cloud depth and darkness, we are speaking of a journey taken by sunlight, a journey lengthened by moisture, a journey interrupted by droplets and crystals suspended in air. The deeper the cloud, the longer the journey. The longer the journey, the dimmer the light that reaches us. And so, the sky grows darker, not abruptly, but gradually, like curtains being drawn layer by layer. And as we glide softly through this understanding, we can almost feel the weight of moisture gathering above. Not oppressive, not frightening, just full. A sky thickened by water, a ceiling deep enough to hold both brilliance at the top and shadow at the base. A reminder that darkness in clouds is often simply depth made visible. As rain begins to fall, the cloud darkens, and now we listen, not just with our eyes, but with our ears, because when rain begins, the sky changes in more ways than one. The first drops may be scattered and tentative, a light tapping on leaves, rooftops, or pavement. The air shifts, the scent of wet earth rises softly, and above, the cloud deepens in tone. We'll listen to the science of why, and the sound of water forming in the sky. Rain begins when droplets inside the cloud grow too large for rising air to support. Through countless gentle collisions, tiny droplets merge into larger ones. As they grow heavier, gravity draws them downward. But the presence of these larger droplets changes the way light moves through the cloud. Small droplets scatter light efficiently and evenly, contributing to brightness in thinner clouds. Larger droplets, however, behave differently. They absorb more light and scatter it in less uniform ways. As rain develops, the cloud contains a greater concentration of these larger droplets. This increases its optical thickness. More light is absorbed or redirected sideways. Less light reaches the underside, and so the cloud appears darker. There is also the simple fact of added density. When rain forms, it means the cloud has reached a high concentration of condensed water. It is saturated, heavy with moisture. The vertical column of droplets and raindrops becomes thicker. This thicker column blocks sunlight more effectively. Imagine light trying to pass through falling rain. Each raindrop bends and reflects it, just as smaller droplets do, but on a larger scale. With millions of raindrops descending simultaneously, the effect becomes significant. The falling rain itself forms a curtain, a veil. From a distance, you can sometimes see this veil hanging beneath a storm cloud, like a grey sheet. That visible rain shaft deepens the darkness below the cloud, because light must now pass through both the cloud base and the falling water. So as rain begins, the sky dims further. But there is something else happening too. When rain falls, it cools the air beneath the cloud. This cooling can create downdrafts, descending currents of air that spread outward when they reach the ground. These downdrafts can lift dust or stir leaves, adding texture to the scene. But more subtly, the cooling reinforces the sense of heaviness in the atmosphere. The air feels thicker, more saturated, and as light fades under the combined effect of cloud depth and falling rain, the world becomes hushed. The sound of rain contributes to this perception. Rainfall creates a continuous, soft noise, a kind of natural white sound. It blankets sharper noises, muting them. The rhythmic tapping on surfaces creates a steady, calming pattern. And psychologically, the dimming light, combined with steady sound, encourages stillness. It feels like the sky has closed itself gently. Scientifically, the darkening is simple. More water means more scattering and absorption of light, more droplets, more raindrops, more depth. But experientially, it feels like a quiet transformation. A bright afternoon turning to silver grey, edges softening, colours cooling, and above it all, the cloud releasing what it has gathered. Rain does not darken the cloud out of mood. It darkens it because the physical presence of falling water changes how light travels. Each drop contributes. Each one bends, reflects, absorbs. Together, they weave a thicker fabric of shadow. And as we listen to the sound of water forming in the sky, droplets colliding, merging, descending, we can imagine the cloud lightening its burden. What grows dark is also what is about to let go. The deepened shadow is the final stage of fullness. And beneath that darkened sky, wrapped in the gentle sound of rainfall, the world feels quieter, safer, slower, held beneath a ceiling of water that has chosen at last to fall. From an airplane, storm clouds are white and bright. From the ground, they loom dark and grey. And now, as we continue our calm journey through the atmosphere, we rise gently above the world below. We imagine ourselves seated by an airplane window, high above the landscape, where the air is thin and quiet, and the earth feels far away. The engine hum is soft, the cabin lights are dim, and outside the window, the sky stretches endlessly. Beneath us, clouds spread out like an ocean, and among them, storm clouds appear, not dark, not moody, but dazzlingly bright. Their tops shine white, almost glowing, as though they are made of snow. This is the gentle paradox of storm clouds. From an airplane, storm clouds are white and bright. From the ground, they loom dark and grey. Let's explore this gentle paradox together. To understand it, we begin with the simplest truth. Clouds are illuminated mostly from above. The sun shines down, and the first part of a cloud that sunlight meets is its top. The upper surface receives direct light, often unobstructed by anything else. The droplets and ice crystals there scatter sunlight efficiently, reflecting much of it back upward. This is why clouds seen from above often look brilliant, especially storm clouds, because storm clouds are thick, tall, and packed with moisture. Their tops contain countless droplets and ice crystals, which act like tiny mirrors and prisms. Sunlight strikes them and scatters in all directions. From above, it is like looking at a glowing field of white. The cloud is reflecting sunlight back toward you. In meteorology, this reflectivity is tied to albedo, the cloud's ability to reflect solar radiation. The higher the albedo, the brighter the cloud appears. And cumulonimbus clouds, with their broad anvils and thick tops, can have very high albedo. They can reflect a great deal of sunlight, appearing radiant against the darker blue of the upper atmosphere. But now, imagine yourself back on the ground. You are no longer above the cloud. You are beneath it. And the underside of a storm cloud is a very different world. The base is often the thickest part, filled with dense concentrations of droplets, growing raindrops, and sometimes falling precipitation. Sunlight entering from above must travel through the entire depth of the cloud to reach the underside. And storm clouds are deep, sometimes miles deep. Along that journey, sunlight is scattered again and again. Much of it is redirected upward or sideways, never reaching the bottom. Some of it is absorbed, warming the cloud slightly. The deeper the cloud, the more light is lost from the downward path. So from below, the base looks dark, grey, charcoal, not because the cloud itself is dark, but because you are looking at the part of it that receives the least direct light. It is similar to standing beneath a thick tree canopy on a sunny day. The leaves above may be glowing bright green in the sunlight, but beneath them, the ground is shaded. The canopy is the same structure, but the light is distributed unevenly. Storm clouds behave in the same way. From above, they glow. From below, they shade. There is also the matter of contrast. When you look down from an airplane, you often see the cloud tops against a darker background, the deep blue of the upper sky, or the distant horizon. Bright white clouds stand out sharply against that darker canvas, making them appear even brighter. From the ground, the cloud base is often seen against the brighter light of the sky around it. Even on a cloudy day, there may be patches of lighter grey or pale blue. This makes the storm cloud's underside appear darker by comparison. Your eyes interpret the difference. The cloud becomes dramatic. The shadow feels deeper. And yet, the cloud itself has not changed. Only your viewpoint has changed. This paradox is one of the quiet wonders of meteorology. The same storm cloud can be both bright and dark, depending on where you stand. It can be luminous above, shadowed below, a glowing mountaintop with a dim valley beneath. And in this understanding, there is something soothing, because it reminds us that darkness is often relative, a matter of perspective, a matter of where the light is falling. From above, storm clouds are bright because they reflect the sun. From below, they are dark because they block it. Both views are true. Both are part of the same structure. And as we imagine the airplane gliding onward, passing above the glowing anvil tops, we can picture the quiet sunlight dancing on ice crystals far below the wing. While beneath the cloud, somewhere on Earth, the land rests in shadow. One storm, two worlds, two perspectives, a gentle paradox floating peacefully between sky and ground. Storm clouds at sunset turn shades of lavender, steel blue, and gold. And now, as the day begins to soften into evening, we arrive at one of the most beautiful moments in the weather's daily rhythm. The sun lowers slowly toward the horizon. Its light grows warmer, longer, more golden. The air cools, the world becomes quieter, and storm clouds, once grey and heavy in midday, begin to change colour. They become painters of twilight. Storm clouds at sunset turn shades of lavender, steel blue, and gold. We'll softly examine how light angle affects cloud colour and mood. To understand this transformation, we begin with the journey sunlight must take. When the sun is high in the sky, sunlight travels through a relatively short slice of atmosphere before reaching the ground. The light remains strong and white, with all wavelengths arriving fairly evenly. But at sunset, the sun's rays must travel through a much longer path of air. The light passes through more molecules, more dust, more water vapor. Along the way, the shorter blue wavelengths scatter away in all directions. This is why the sky around sunset often glows orange or red. The remaining light is richer in warm tones. Now imagine that warm, slanting light striking a storm cloud. Because the sun is low, it no longer shines directly downward onto the cloud's top. Instead, it illuminates the cloud from the side, painting its edges with colour. One side of the cloud may glow gold, the other side may remain in shadow, deepening into blue-grey. And in between, gradients appear, soft blends of peach, rose, lavender, and steel. The cloud becomes a three-dimensional sculpture of light. Its billows catch the sun like mountain ridges. Its valleys hold shadow like quiet caves. And because storm clouds are thick, the light doesn't pass through them easily. It strikes the surface and scatters, reflecting outward in warm hues. The interior remains dim, making the contrast more dramatic. This is why cumulonimbus clouds at sunset can look almost cinematic, like towering castles lit by the last fire of day. The anvil top may catch sunlight strongly, glowing pale gold or bright white. The base may remain dark, appearing like a heavy band of slate. And sometimes, the underside reflects faint, warm tones too, as light bounces off the ground or surrounding clouds. Even the rain shafts beneath the storm can take on colour. If the sun is positioned just right, falling rain may glow softly in amber streaks, while the surrounding air turns cool and blue. It is as if the storm is both night and day at once, a twilight structure, a meeting place between warmth and shadow. The mood of a storm cloud at sunset is often different than during the day. In midday, the dark base can feel stark because the world around it is bright. But at sunset, the whole landscape is already dimming. The darkness feels more natural, more gentle. The colours are softer, and the light is less harsh. This is why storm clouds can feel strangely peaceful at dusk. Their shadows blend into the evening. Their outlines become less sharp. The storm's presence becomes part of the slow fading of the day. And in that fading, the sky feels calmer. The storm cloud is no longer simply grey. It becomes layered with colour, as if it is holding the last warmth of sunlight in its upper edges. Lavender appears when sunlight mixes with scattered blue light. Steel blue appears in the shadowed regions, where little warm light reaches. Gold appears where the sun strikes directly, illuminating droplets and ice crystals. All of these colours are born from angle, from the sun's low position, from the longer path of light through the atmosphere, and from the cloud's own depth and texture. So the storm cloud at sunset is not changing its substance. It is still water, still ice, still air. But the light has changed, and the light changes everything. The storm becomes softer in tone, more dreamlike, more painterly. And as we watch it from the ground, the sky slowly shifting through its evening colours, we can feel the day releasing itself. The storm cloud, glowing faintly in gold at the edges, becomes part of the sunset's quiet ceremony. A towering shadow, a glowing crown, a soft gradient of lavender and steel. And beneath it all, the earth grows dim and calm, as if the world is being gently tucked into night. A storm cloud may look darker if it floats near a bright cloud. And now, as we continue our unhurried drift beneath the wide dome of the atmosphere, we notice something subtle, something that does not belong only to the cloud itself, but to its surroundings. Because no cloud exists alone. Each one floats within a larger canvas of sky. Blue expanses, pale veils of cirrus, soft clusters of cumulus glowing in sunlight. And sometimes, the drama we perceive is not created by the storm cloud alone, but by contrast. We'll explore how contrast and context paint the drama of the heavens. Imagine a bright afternoon sky where fair weather cumulus clouds drift like white sails. their edges are illuminated sharply by direct sunlight. They appear brilliant, almost luminous against the blue. Now imagine that, in the distance, a taller cloud begins to rise. It gathers depth, its base thickens, its interior fills with moisture. Soon, it grows into a towering cumulonimbus, its underside deepening into grey. Placed beside the bright cumulus, the storm cloud looks dramatically darker. But here is the gentle truth. Its darkness may not have changed at all. What has changed is what surrounds it. Our eyes are always comparing brightness. When we look at something, we do not measure its light in isolation. Instead, our vision interprets tone relative to nearby objects. A medium grey can look almost black when placed next to white. A pale grey can look nearly white when placed beside charcoal. This is called simultaneous contrast, a principle of perception where adjacent tones influence how we see one another. So, when a storm cloud floats near a bright cloud, the brightness of the neighbour amplifies the darkness of the storm. The white cloud reflects sunlight efficiently, sending brilliance toward your eyes. The storm cloud, thick and dense, reflects less light downward. Side by side, the difference becomes striking. The sky becomes a stage for contrast. There is also the matter of background. A storm cloud viewed against a clear blue sky often appears darker because the blue is luminous and open. The eye reads the blue as light-filled, making the grey beneath the storm appear heavier. But if the entire sky is overcast, if layers of grey stretch in every direction, the same storm cloud might not stand out as dramatically. Its tone blends more gently into the surrounding atmosphere. Context shapes perception. The heavens are painted not only with clouds, but with relationships between them. One cloud brightens another. One shadow deepens the next. Even the position of the sun matters. If sunlight breaks through a gap and illuminates part of the sky, while leaving another part shaded, the illuminated region becomes radiant by comparison. The shaded region feels darker than it would alone. This is why storm clouds near sunlit edges can appear so cinematic. The rim of light along their borders glows intensely, while their interiors appear even more profound in contrast. And yet, if you were to isolate that storm cloud, place it alone against a neutral sky, it might seem softer, less dramatic. There is something calming in recognizing this, that the sky's drama is often a conversation between shapes and light. That darkness can be amplified simply by proximity to brightness. It is not always an increase in shadow, but an increase in comparison. Even rain shafts can deepen this effect. A streak of bright sunlight beside a curtain of falling rain makes the rain appear darker than it might otherwise be. The heavens become a composition of tones, light and shade in dialogue. And as we lie back, watching clouds drift slowly across the horizon, we can notice how the sky is rarely uniform. There are always gradations, brighter patches, softer shadows. Storm clouds do not create their mood alone. They are shaped by context, by the brightness of neighboring clouds, by the clarity of surrounding sky, by the angle of light touching them. So, when you see a storm cloud that looks especially dark, you might gently ask, what is beside it? What brightness is helping to define its shadow? Because sometimes, the drama of the heavens is less about intensity and more about contrast. A painting made of relationships, a sky where light and dark lean against one another. And in that leaning, they create the quiet beauty of depth and dimension above us. Sometimes it's not the cloud, but our own eyes. And now, as we continue our calm meditation beneath gathering skies. We turn inward, not to the cloud above, but to the eyes observing it. Because perception is not only about physics, it is also about biology. As light dims, our perception shifts. Let's gently explore the science of sight beneath gathering clouds. Imagine standing outdoors as a storm cloud drifts overhead. At first, the world is bright. Your eyes are adjusted to sunlight. The pupils are small, narrowing to limit the amount of light entering. The cells in your retina, called cones, are active, allowing you to see vivid color and sharp detail. Then the cloud thickens. Sunlight fades. The sky turns from bright blue to muted gray, and your eyes begin to change. The pupils slowly widen, allowing more light to enter. This happens automatically, without thought. It is part of your body's quiet adaptation to dimmer conditions. At the same time, another subtle shift occurs. Your retina contains two types of light-sensitive cells, cones and rods. Cones function best in bright light and are responsible for color vision. Rods function better in low light and are more sensitive to brightness and motion, but they do not perceive color as clearly. As the sky darkens, the cones become less active, and the rods begin to take on a greater role. This transition is called dark adaptation. It does not happen instantly. It unfolds gradually over minutes. During this shift, colors may appear less vibrant. Blues and greens may seem stronger than reds, because rods are more sensitive to shorter wavelengths. This is why a storm cloud at dusk can look especially blue or steel-toned. Your eyes are adjusting, and because the rods are more sensitive to contrast, the differences between light and shadow may feel more pronounced. The cloud may seem darker than it truly is, not because it has changed significantly, but because your vision is interpreting it differently. There is also the matter of expectation. When we see a storm cloud forming, our minds anticipate dimness. We expect rain. We expect shadow. This anticipation can subtly influence perception, making the cloud appear heavier or darker. But physically, what is happening is simple. The light level has dropped. Your pupils have widened. Your retinal chemistry has shifted, and your visual system is recalibrating to new conditions. Sometimes, after standing beneath a dark cloud for a few minutes, you may notice that the world begins to feel brighter again, even though the cloud has not moved. This is because your eyes have completed part of their adjustment. What once felt very dark now feels manageable, even soft. This is adaptation at work. Your vision seeks balance. It constantly adjusts to maintain clarity. There is something deeply comforting about this, that even as the sky dims, your body responds with gentle precision. Your eyes widen to welcome more light. Your rods activate to sense the world in shadow. Your perception shifts to match the atmosphere. So sometimes, when a storm cloud feels especially dark, it is not only the cloud, it is the interplay between light and eye, between atmosphere and retina, between sky and perception. And as we stand beneath gathering clouds, feeling the air cool and watching the light fade, we can appreciate this quiet partnership. The cloud dims the day, the eye adjusts. Together, they create the mood of the moment. Not harsh, not overwhelming, just a gentle lowering of brightness, met by a gentle widening of sight. And in that soft exchange, the world remains visible, still, calm, held beneath the grey ceiling of the sky, and seen through eyes that know how to adapt. Let's climb into the dreamscape of a growing thunderhead, layer by layer, watching how its shadow deepens the earth below. And now, as the afternoon warmth gathers quietly across fields and rooftops, we turn our gaze toward the horizon. There, a small white cloud begins to rise, at first no different from the others. A gentle cumulus, rounded and bright, drifting without urgency. But beneath it, warm air continues to lift. The ground, warmed by sunlight, releases invisible currents upward. These rising pockets of air carry moisture skyward, and as they cool, that moisture condenses into droplets. The cloud swells. It rises not in haste, but in steady ascent, layer by layer. The once modest cloud begins to stretch vertically. Its top billows upward, folding over itself like soft peaks forming in slow motion. Sunlight still catches its upper edges, illuminating them in brilliant white. Below, however, something subtle changes. As the cloud deepens, its base grows denser. More droplets gather. Light entering from above must travel through greater thickness before reaching the underside. Some of it is scattered away, some reflected upward. Less light arrives at the ground, and so a faint shadow begins to form beneath the rising tower. We continue climbing into this dreamscape. Higher still, the cloud pushes into cooler layers of the atmosphere. The air surrounding it becomes colder with height, allowing the rising column to remain buoyant. The thunderhead grows taller, more defined. From within, the view is soft and luminous. Droplets shimmer in diffused sunlight. The interior feels vast but gentle, like drifting inside a cathedral of mist. Outside, on the earth below, the light dims further. The shadow is not sharp-edged like that of a building. It is gradual, spreading softly across the landscape. Colors deepen, greens turn richer, whites become muted. The growing thunderhead casts a broad, moving canopy over fields and towns. Its shadow deepens because its height increases. The taller the cloud, the more sunlight it intercepts. The greater its vertical development, the larger the area beneath it that falls into shade. Eventually, the cloud reaches the upper boundary of the troposphere. There, where the air becomes more stable, its upward climb slows. Instead of rising further, the top spreads outward, forming the familiar anvil shape. But the base remains dark, and the shadow below continues to widen. The thunderhead is now a towering presence, bright and glowing at its summit, dim and brooding at its base. Yet even now, its growth is a natural consequence of warmth and moisture meeting cooler air above. It is not abrupt, it is architectural, each layer added through condensation, each level shaped by rising currents, each increase in depth increasing its capacity to block sunlight. As we hover gently within this towering structure, we can imagine the earth beneath it. Birds quieting, winds shifting, the temperature cooling slightly under the expanding shade. The thunderhead becomes a floating mountain, casting a slow-moving dusk. But the beauty of it remains, because even as its shadow deepens the earth below, its upper reaches remain luminous. Sunlight still touches the high ridges of vapor and ice, painting them bright against the blue sky. Light and shadow exist together within the same cloud. The thunderhead rising is not merely darkening the world, it is reshaping the light. It is redistributing brightness and shade across space. And as we gently descend from its heights, returning to the shaded ground below, we carry with us the understanding that this deepening shadow is simply the result of vertical growth. Warm air rising, moisture condensing, a cloud building itself toward the sky, and beneath it, the earth resting quietly in its passing shade. As storms mature, cool air descends, and now, as the thunderhead reaches its fullest form, something begins to shift within it. Rising motion continues in some regions, but elsewhere, another movement begins. Air that has risen high into the cloud cools significantly. Some of it loses its buoyancy. Rain falling through the cloud drags air downward with it, creating descending currents. These are called downdrafts, and they are part of the storm's quiet balance. We'll drift downward with them, into darker skies and heavier air. Imagine floating high within the storm, where ice crystals swirl gently and droplets collide. As rain begins to fall more steadily, it pulls surrounding air with it. This air, cooled by evaporation and melting, becomes denser than the warmer air around it. Denser air sinks, and so begins our descent. We drift downward through the cloud's interior, carried by this cool descending current. The light grows dimmer as we move lower. The droplets around us grow larger. The sound of rain becomes more pronounced. Downdrafts are not violent in every storm. Often they are steady, controlled movements of air seeking equilibrium. As this cooler air reaches the lower layers of the cloud, it spreads outward. When it reaches the ground, it may create a gentle outward flow known as a gust front. But from within, it simply feels like a calm downward glide. The sky above grows darker because the storm has reached maturity. At this stage, the cloud is at its thickest. Rain is falling, moisture is abundant. The combination of dense droplets and descending air increases the cloud's opacity. Less sunlight penetrates through the layers. The base becomes more uniform in tone, often a smooth grey sheet stretching across the sky. As we continue drifting downward, the temperature drops slightly. The air feels heavier, not in weight alone, but in moisture content. Humidity rises as rain evaporates into the surrounding air. This increased moisture further scatters light. The sky dims, not only because of the cloud's depth, but because of the saturated air beneath it. Evaporation within downdrafts can cool the air significantly. This cooling reinforces the descending motion, maintaining the flow of air downward. It is a cycle. Rain pulls air down, cool air sinks. The sinking air spreads and stabilizes the lower atmosphere. And above, the cloud gradually begins to lose its upward momentum. The dimming sky reflects this transition. The storm has moved from growth to release. The brightest sunlit towers may still glow faintly at the edges, but beneath them, the interior becomes darker and more uniform. From the ground, this feels like the heart of the storm, the moment when the sky is most overcast, when rain falls steadily, when the air feels thick and cool. Yet even here, there is balance. Downdrafts help regulate the storm's life cycle. They prevent endless growth. They redistribute heat and moisture. They mark the beginning of the storm's eventual softening. And as we drift gently to the ground with the cool descending air, we notice how the world has changed. The light is muted, the air is cooler, the scent of rain fills the space between earth and sky. But there is calm in this dimness, because downdrafts, like updrafts, are part of the atmosphere's natural rhythm. Air rises, air falls, moisture gathers, moisture returns. And the dimming sky is simply the visual expression of this process, a deepening grey born from density, rain, and descending cool air. As the storm matures, the world beneath it rests in shadow, not in fear, not in urgency, but in a softened light shaped by falling water and cooling air. And in that gentle descent, the sky grows quiet, and the earth waits patiently beneath its drifting shade. Often, darkness precedes rainfall, And now we arrive at a moment that feels almost suspended in time. The air is still. The wind, which once moved gently through trees and across open fields, seems to hesitate. Leaves pause in place. Birds grow quieter. The world feels as though it is holding a slow, patient breath. Above, the sky deepens. The storm cloud has gathered itself fully. Its base is thick, its layers dense with moisture. The light that once filtered through in softened tones now fades further. Often, darkness precedes rainfall, but this darkness is not sudden. It is gradual, a lowering of brightness, minute by minute. We'll rest here in that timeless pause and study why the skies seem most brooding just before they break. Before rain begins to fall, the cloud must reach a certain fullness. Droplets inside must grow large enough to overcome the upward currents holding them aloft. The cloud thickens as this process unfolds. As it thickens, its optical depth increases. More water droplets mean more scattering and absorption of sunlight. Light entering from above struggles to pass through the layered interior. The underside becomes a broad, even grey. The sky dims. But there is another reason this moment feels darker than others. As the storm approaches, high clouds often arrive first, thin veils that soften the sun long before the main body of the storm arrives. Then, mid-level clouds follow, adding to the coverage. Finally, the dense base of the cumulonimbus spreads overhead, layer upon layer. By the time rain is ready to fall, the sun may be completely obscured by multiple strata of moisture. The dimming is cumulative. Each layer subtracts a little more light. And so, just before the first drop falls, the sky can appear at its deepest shade. There is also a subtle change in the air itself. Humidity rises as the storm nears. Moisture increases in the lower atmosphere. This added water vapor scatters light even before rain begins. The entire sky can take on a muted tone, as if viewed through a gentle filter. The world below responds. Colors deepen, shadows soften. The temperature may drop slightly as the cloud blocks direct sunlight. And in this pause, this quiet, brooding moment, there is a sense of expectancy, not tension, just fullness. The cloud has gathered warmth from the ground, lifted moisture upward, condensed it into droplets. It has built itself carefully, layer by layer. Now it hovers at the threshold of release. The darkness we perceive is simply the visual sign of that fullness. The cloud is at its most saturated. Its base is at its thickest. The journey of sunlight downward is at its longest and most interrupted, sometimes distant. Rain shafts can be seen already falling from one edge of the storm, while the area beneath you remains dry. The sky darkens further as that curtain of rain approaches. The calm before the rain is often characterized by stillness because the main downdrafts have not yet reached the ground. The air feels heavy, humid, quiet, and in that quiet, the dimness feels deeper. We rest here, in the pause between gathering and release, in the hush before the soft percussion of raindrops begins. Scientifically, this moment is the culmination of condensation and growth. The droplets have merged, grown, and prepared to descend. Optically, it is the moment when the cloud is thickest and most effective at blocking sunlight. Emotionally, it feels reflective, introspective. The sky's lowered brightness encourages stillness. And then, almost gently, the first drop falls. The calm gives way to rhythm. But for that brief space of time before it begins, the darkness holds steady. A full cloud, a quiet earth, a breath suspended between light and rain. And in that timeless pause, the sky seems most brooding, not because it is angry, but because it is complete, ready to release what it has gathered. Let's float beside the edge of a storm front, watching light dim as shadow overtakes the sun, slowly, softly. And now we imagine ourselves not beneath the center of the storm, but at its boundary, the edge, where sunlight still spills across the land, where brightness and shadow meet. In the distance, the leading edge of the storm cloud approaches. Its underside is smooth and grey, its upper towers glowing faintly where sunlight still touches them. The sun, still visible, begins to share the sky with the approaching mass. At first, nothing seems dramatic. The light remains strong, the world is illuminated, but gradually the cloud's edge moves closer to the sun's position in the sky. And as it does, something gentle begins to happen. Light dims, not abruptly, but as though a slow veil is being drawn across the sun. When clouds overtake the sun, the effect depends on thickness and position. A thin cloud may only soften the brightness, creating a diffused glow. Shadows on the ground blur and fade. But a thick storm cloud acts more decisively. Its leading edge can block direct sunlight entirely. We float beside this advancing boundary. Half the landscape is still bathed in light. The other half rests in shade. The dividing line moves steadily forward. This transition feels dramatic because our eyes are highly sensitive to changes in brightness. Even a moderate reduction in sunlight can feel significant when it occurs over seconds or minutes. The shadow does not fall like a curtain snapping shut. It glides, it expands. The sunlight weakens as the cloud moves between Earth and Sun, intercepting the direct rays. Without direct sunlight, the ground receives only diffuse light scattered from surrounding sky. This light is softer and less intense. Colors cool slightly, edges lose contrast. The world feels calmer. At the edge of a storm front, this process can be especially striking. The cloud wall may appear thick and defined, its underside darker than the open sky ahead of it. As it overtakes the sun's position, the brightness transitions into grey. This is pure geometry. The cloud blocks the line of sight path between sun and surface. Direct rays are interrupted. Diffuse light remains. Sometimes, sunlight can be seen streaming around the edges of the cloud, creating beams of light, known as crepuscular rays. These shafts of brightness radiate through gaps, illuminating patches of land while others remain shaded. This interplay creates movement in light and shadow, a slow choreography across fields and rooftops. And as we float beside this edge, watching the shadow overtake the sun, we notice how gradual it truly is. There is no snap, no sudden plunge into darkness. Even thick storm clouds take time to move into position. The earth rotates slowly. Clouds drift with prevailing winds. The dimming unfolds like a long exhale, and with each passing moment, the light level adjusts. The sun becomes a pale glow behind layers of moisture, then a brighter spot behind grey, then completely obscured. The sky settles into uniform tone. There is something peaceful in witnessing this overtaking, because it reminds us that change in the atmosphere is often steady and continuous. The storm front advances, but it does so within the rhythm of wind and pressure patterns. The dimming of sunlight is a natural consequence of interception and scattering. And beneath this advancing shade, the air may cool slightly. The scent of approaching rain becomes noticeable. The world prepares, but gently. As the cloud fully overtakes the sun, the transition completes. Direct sunlight is gone. Diffuse grey light remains. The storm has claimed its space in the sky. And yet, Even now, above the cloud, sunlight continues to shine. It is simply hidden from view. We rest at the boundary, watching brightness give way to shadow, not with alarm, but with quiet observation. Light dimming, shadow spreading, a slow, soft overtaking. And in that movement, the sky reveals its rhythm once more, steady, patient, and beautifully gradual. We'll explore how advancing warm or cold fronts bring dramatic sky changes, deepening cloud layers that darken the world. And now, as we continue our slow meteorological bedtime journey, we begin to zoom outward, away from a single storm cloud, away from one thunderhead rising in the distance, and towards something larger, something that stretches across entire regions. A front. A weather front is not a wall or a line you can touch. It is a boundary between air masses, two bodies of air with different temperatures, different moisture levels, and different densities. When one air mass meets another, the atmosphere must adjust, and that adjustment often shows itself in the sky. We'll explore how advancing warm or cold fronts bring dramatic sky changes, deepening cloud layers that darken the world. Let's begin with a warm front. A warm front happens when warm air slowly advances toward cooler air. Warm air is lighter, so it cannot easily push the cooler air out of the way. Instead, it rises gently over it, like a soft blanket sliding upward. This rising motion is gradual and widespread. As the warm air rises, it cools, and the moisture inside condenses into clouds. The clouds of a warm front often arrive in layers. First, you might see high, thin cirrus clouds, wispy streaks far above, barely shading the sun. They often appear bright and delicate, like brushed silk across the sky. Then, as the front draws closer, the clouds thicken into cirrostratus, creating a pale veil that can produce halos around the sun or moon. Still later, the cloud deck lowers into altostratus, grey sheets that cover more of the sky, muting the sunlight and softening shadows. And eventually, nimbostratus clouds may form, thick, dark layers that bring steady rain. In this slow progression, the sky gradually dims, not suddenly, not dramatically, but with a steady deepening, as if the atmosphere is turning down the light one layer at a time. A warm front is often peaceful in its approach. The rain it brings tends to be gentle and sustained. The sky becomes uniformly grey, and the world beneath it feels calm and quiet. Now let's turn to a cold front. A cold front is different. Cold air is heavier and denser. When it advances, it pushes beneath warm air like a wedge. The warm air is forced upward more quickly. This rapid lifting can create more dramatic cloud structures. Tall cumulus clouds may grow into cumulonimbus. The sky can shift quickly from clear to turbulent, from bright to shadowed. Cold fronts often bring sharp changes, gusty winds, brief heavy rain, and rapid temperature drops. But even here, the process is still rooted in gentle physics. Air masses meeting, warm air rising, moisture condensing, cloud layers thickening. In the hours before a cold front arrives, the sky may begin with scattered cumulus clouds, bright and sunlit. Then, the clouds become larger, more numerous, and darker underneath. A line of towering clouds may appear along the front's edge, like a distant wall of rising mist. As the front passes, the world beneath may darken rapidly. Light becomes filtered, then blocked. Rain curtains fall. The sky becomes a moving ceiling of grey. And after the front passes, the clouds often break apart, leaving behind cooler, clearer air. So both warm and cold fronts reshape the sky, but in different rhythms. Warm fronts bring gradual dimming. Cold fronts bring sharper transitions. Both create cloud layers that deepen and darken the world. Because when air rises, clouds form, and when clouds thicken, sunlight is scattered and absorbed. This is why advancing fronts often feel like changes in mood. The sky's brightness is one of the most powerful signals we perceive. When it changes, we sense that something is shifting, even if we don't know the scientific details. Fronts are the atmosphere's way of redistributing heat. Warm air moving poleward, cold air moving equatorward, a constant balancing act across the planet. And the clouds we see are the visible signature of that balancing. So, when a front approaches and the sky grows layered, when the light dims and the horizon becomes hazy, you are witnessing the slow meeting of air masses. A gentle collision, a quiet lift, a deepening of cloud layers that turns sunlight into softness. And as we rest beneath these shifting skies, we can feel how fronts bring not only weather, but atmosphere, an enveloping sense of transition. The world becomes muted. The air changes texture. The sky grows heavy with moisture. And in that deepening grey, the earth is invited to slow down and listen as the next chapter of weather arrives. We drift beneath the mysterious mammatus, pouch-like formations that hang beneath thunderclouds. And now, as the storm cloud above us reaches its fullest maturity, we notice something unusual along its underside. Instead of a smooth base, the cloud appears textured, as though it has pockets, rounded bulges, soft hanging shapes. They look like inverted hills made of vapor, drooping downward from the belly of the thunderstorm. These are mammatus clouds. They are some of the most striking formations in the sky, and yet they can feel oddly peaceful to watch. They hang there like slow, suspended lanterns. Like the sky has grown a pattern of gentle pouches. We drift beneath them, gazing upward, and feel their strange beauty. Shadows of texture and tension. Mammatus clouds form most often beneath the anvil of a cumulonimbus cloud, high, spreading, icy regions of a thunderstorm. They are associated with strong storm systems, but the mammatus themselves are not the storm's violence. They are simply a sign of complex air motion, a sculpted underside. To understand how they form, we begin with the idea of sinking air. Most clouds form when air rises, cools, and condenses, but mammatus are connected to descending pockets of cooler air. Within the anvil region, the air is often saturated with ice crystals and droplets. Some regions become slightly cooler and heavier than the surrounding air. When that happens, small parcels of air begin to sink. As they sink, they carry moisture with them. These descending pockets form rounded bulges because they are sinking unevenly, like soft blobs of cooler air slipping downward into warmer layers below. As they descend, the moisture may evaporate or sublimate, cooling the air further. This cooling can reinforce the sinking motion, allowing the pouch shape to become more pronounced. So, mammatus clouds are created by a delicate interplay. Cool air sinking, moisture evaporating, shapes forming along the underside of the storm. The result is a textured sky, filled with hanging domes of vapor. From below, mammatus often appear dramatic because of how light interacts with their curves. The bulges catch sunlight differently than the flatter regions around them. One side may be illuminated softly, while the other side falls into shadow. This creates depth, a three-dimensional effect. The cloud looks like sculpted stone, yet it is made entirely of air and water. The shadows beneath mammatus can feel like quiet tension in the sky, not the tension of fear, but the tension of contrast and form. The sky is not smooth, it is patterned, and patterns draw our attention. Sometimes mammatus appear during sunset, when the light is low and golden. In those moments, the pouches can glow with warm orange tones, while their shadows deepen into purple-grey. The sky becomes painterly, almost surreal, like a dreamscape unfolding overhead. And yet, the science remains simple and gentle. Air sinks in pockets. Moisture condenses and evaporates. The underside of the anvil becomes textured. Mammatus clouds remind us that the atmosphere is not only about upward motion. It is also about descent, about cooling, about gravity shaping air in slow, invisible ways. They are the downward echoes of a storm's great upward towers, a quiet counterpart to the rising thunderhead. And as we lie beneath them, we can appreciate how soft they look despite their dramatic shape. Their edges are rounded, smooth, almost pillow-like. They do not rush. They hang in place, slowly shifting. Their shadows deepen and lighten as the sun moves behind them. They are texture made visible, tension made gentle, a sculpted underside of the storm. So, when you see mammatus clouds, you are seeing the storm's upper world reflected in its base. You are seeing the atmosphere folding into itself, sinking and shaping moisture into pouches that dangle like slow ornaments. And beneath them, the world feels hushed, the light filtered, the sky alive with pattern, not harsh, not frightening, just mysterious. A reminder that even storms create beauty in their quiet moments, and that the underside of the heavens can be as detailed and delicate as the top. Mammatus clouds, shadows beneath, soft pockets of sky, hanging calmly above the earth, as if the storm itself has decided to dream. Sometimes rain falls and evaporates before reaching the ground. And now, as we continue drifting through the quiet theatre of the atmosphere, we notice something delicate beneath the clouds, something that looks like rain, but feels almost ghostly. From a distance, thin streaks descend from the base of a cloud. They fall in soft vertical lines, like pale threads unraveling from the sky. They resemble rainfall, yet the ground below remains dry. This gentle phenomenon is called virga. Virga is rain that begins its journey downward, but never completes it. It forms inside the cloud as droplets grow large enough to fall, and then it descends through air that is too dry to allow it to survive. The droplets evaporate before they reach the surface, and so the rain disappears into the air, leaving only its faint signature in the sky. We'll explore these soft shafts of rain and the way they darken the cloud that holds them. To understand virga, we begin with the dryness of the lower atmosphere. Even on a day with clouds overhead, the air beneath them can sometimes be surprisingly dry, especially in desert regions, high plains, or during certain warm weather patterns. In these conditions, moisture may be plentiful in the cloud itself, but scarce below. When raindrops fall out of the cloud and enter this dry air, they begin to evaporate. Evaporation is a cooling process. As water changes from liquid into vapor, it absorbs heat energy from the surrounding air. This cools the air and also causes the raindrops to shrink. As the drops shrink, they become lighter and may evaporate even faster. Eventually, they vanish completely. But even though the rain disappears, the virga remains visible because of light. The falling droplets scatter sunlight, creating those pale streaks we can see from afar. The streaks may look silvery or grey, sometimes even tinted with sunset colours. Virga often appears as soft curtains hanging beneath a cloud, but with edges that fade gradually instead of reaching the ground. And there is something strangely calming about it. It feels like the sky is trying to rain. But the earth is not ready yet. Like water is being offered, and then taken back into the air. But Virga is not wasted. It moistens the atmosphere beneath the cloud. Each evaporating droplet adds water vapor to the lower air, slowly increasing humidity. Over time, this can help future rain reach the ground. Virga is the sky's way of testing the air. A gentle experiment in moisture. And it also affects the cloud above. When droplets fall out of a cloud, whether they reach the ground or not, the cloud is losing some of its suspended water. But during the moment when Virga is visible, the cloud often appears darker. Why? Because the cloud is thick enough to produce precipitation, even if that precipitation evaporates below. That means the cloud contains high moisture content and strong vertical depth. It is already dense, already layered, already scattering and absorbing sunlight more strongly than a thin cloud would. And the Virga itself contributes to the darkening effect. Those falling streaks scatter light away from your eyes. They create a hazy curtain beneath the cloud, reducing the amount of sunlight that can travel cleanly downward. Even though the rain does not reach the ground, it still blocks and diffuses light on its way. So, the cloud appears heavier, darker, more full. Sometimes, Virga can create visible downdrafts. As evaporation cools the air, that cooler air becomes denser and begins to sink. This can cause subtle shifts in wind at the surface, sometimes creating gusty breezes, even without rainfall. But in our calm journey, we imagine it softly. A gentle descent of cooled air, a slow drifting of invisible currents, a quiet stirring beneath the cloud. Virga reminds us that weather is not always complete. Not every process reaches its final step. Sometimes the sky begins a story and then lets it fade before the ending. Rain forms, rain falls, rain dissolves, and still the cloud remains above, drifting onward. So, when you see those pale streaks of Virga hanging beneath a dark cloud, you are witnessing evaporation in motion. You are seeing water returning to air. You are seeing light scattered through falling droplets that vanish before they touch the earth. It is one of the atmosphere's quietest performances. A rainfall that never arrives. A soft curtain that dissolves into the wind. And beneath it all, the world remains dry but dimmed, resting under a cloud that has gathered enough moisture to rain. Even if the rain itself is only a brief, fading whisper in the sky. Hot days build towering storm clouds. And now we turn our attention to summer, the season when the sky seems to stretch taller, when afternoons shimmer with heat, and when storms appear with a kind of grand, sculptural beauty. Summer thunderstorms often look larger than life. Their towers rise high and sharp. Their shadows are deep. Their edges glow in brilliant white against the intense blue of warm season skies. And even when they are far away, they can look dramatic, like castles forming on the horizon. We'll gently explore why summer skies often hold the darkest, most vivid thunderheads. The answer begins at the surface of the earth. In summer, the sun is high and strong. Daylight lasts longer. The ground absorbs more heat energy, warming the air above it. This creates a deeper layer of warm, buoyant air near the surface. Warm air rises more easily, and when warm air rises, it fuels convection, the upward motion that builds thunderstorm clouds. So in summer, the atmosphere has a powerful engine. Heat provides lift, and moisture often provides fuel. In many regions, summer air holds more water vapor. Warm air can carry more moisture than cold air. So humid summer days often contain abundant invisible water. When this moist air rises and cools, condensation occurs rapidly, producing thick clouds. And because the rising motion can be strong, the cloud can build vertically at impressive speed. This is why summer storms often form towering cumulonimbus clouds. They rise high into the troposphere, sometimes reaching the tropopause and spreading into wide anvils. Their vertical depth becomes enormous, and depth creates darkness. The taller and thicker the storm cloud becomes, the more light it blocks. Sunlight enters from above, but it cannot easily travel through miles of moisture. It is scattered and absorbed. The base grows charcoal grey. The underside becomes shadowed and heavy-looking, but summer skies also enhance contrast. In summer, the surrounding atmosphere is often clearer. The sky can appear a rich, saturated blue when conditions are fair. Against that blue, a towering storm cloud appears even more intense. Bright white tops against deep blue sky, dark grey bases against sunlit landscapes. This contrast makes the storm look dramatic. It becomes a bold shape in a vivid setting. Summer sunlight itself is also more direct. With the sun higher overhead, cloud tops receive intense illumination. This can make the upper edges of a cumulonimbus look brilliantly bright, almost glowing, while the base remains dark. So summer storms often display extreme contrast within a single cloud, radiant crowns and shadowed bellies. And the atmosphere in summer is often unstable. Instability means that rising air continues rising because it remains warmer than the air around it. On hot days, the difference between warm surface air and cooler upper air can be significant, allowing updrafts to build tall towers. This instability contributes to rapid cloud growth. The cloud becomes a vertical monument of rising energy. Summer storms also tend to be localized. Instead of broad, layered grey skies, summer thunderstorms often rise as isolated towers surrounded by clear air. This makes them stand out even more. A single cumulonimbus cloud can dominate the horizon, rising like a mountain, while the rest of the sky remains open. That isolation enhances its drama. A storm cloud in a clear summer sky looks sharper, taller, more defined than one embedded in widespread overcast. And because summer storms often produce heavy rain, their bases become dense with large droplets and precipitation curtains. These falling rain shafts add additional darkness beneath the cloud, creating streaked shadows and grey veils. So, the storm becomes both sculpted and shaded. A dramatic shape carved by sunlight above and rain below. But even as we speak of drama, we keep our tone soft, because summer storms are not only powerful, they are also beautiful. They are the atmosphere's way of releasing built-up heat. A natural exhale. The warm earth sends energy upward, and the sky responds by building clouds tall enough to carry that energy away. The storm cloud rises, spreads, and rains. And afterward, the air often feels cooler and cleaner. So when you see a vivid summer thunderhead towering over the horizon with its dark base and bright crown, you are seeing the result of heat, moisture, and instability working together. Hot ground lifting warm air, moisture condensing into depth, sunlight illuminating the top while shadow deepens below. A summer sky creating one of its grandest sculptures, a dramatic thunderhead, standing tall, quietly gathering, and painting the atmosphere with contrast and beauty. as the season of warmth breathes upward into the sky. Humidity changes how light scatters. And now, as we continue to drift through the atmospheric layers in our calm exploration of clouds and sky, we arrive at something less visible but deeply felt: humidity. Humidity is the amount of water vapor in the air. It is not something we can see directly, but we sense it in the warmth that feels thick on the skin, in the softness of the air before a storm, in the way distant hills seem hazy on a humid afternoon. Tonight, we gently drift through moist air and explore how humidity mutes and deepens storm tones, shaping the color of the clouds that dominate our sky. Imagine a day when the air feels heavy with moisture, long before clouds form. The humidity is high. Each molecule of air carries more water vapor. This extra moisture affects how sunlight travels through the atmosphere. Sunlight entering humid air collides with more water molecules and vapor. Instead of passing straight through the sky to your eyes, light is scattered, tiny deflections that redirect rays in all directions. This scattering softens the intensity of direct sunlight. The sky appears paler. Edges of objects become less sharp. Colors become gentler. When humidity is low, the opposite happens. The air is clearer. Light travels more directly. Colors are crisp. Shadows are sharp. But when humidity rises, as it often does before a storm, light takes a more hesitant path. It meets resistance in the form of additional water vapor. It scatters. It diffuses. This diffusion alters the way we see clouds. Clouds at high humidity levels can appear softer, smoother, and slightly grayer than they would in dry air. The water vapor around them acts almost like a filter, muting contrasts and blending tones. Now, let us imagine ourselves lying in a field beneath gathering storm clouds. The air feels warm and thick against your skin. There is a slight sheen of moisture on the breeze. You look up and notice that the clouds are not simply grey. They have a depth of tone that seems broader and more diffuse than clouds you've seen on a crisp, dry day. This is because the humid air around and beneath the cloud is interacting with light. Not only is the cloud itself scattering light with its droplets, but the surrounding moist air is contributing to that effect. Light rays, as they travel downward through the humid layer, encounter water vapor. Each small encounter slightly alters the ray's direction. The cumulative effect is a softening of light before it even reaches the cloud's base. When that diffused light meets the dense underside of a storm cloud, it is reflected and scattered again, creating tonal variations that can feel deeply muted, like greys softened by a wash of moisture rather than stark shadows laid in ink. This interaction between humidity and light often makes the colors of a storm cloud more subtle. Instead of dramatic contrasts between bright white tops and dark grey bases, you may observe a wider palette of gentle shades in between: cool silver, misty blue-grey, pearly lavender, soft charcoal. These tones do not signal intensity or danger. They signal the rich presence of moisture in the atmosphere. Humidity also changes how we perceive the space between clouds and ground. When the air is humid, heat and moisture near the surface can create a slight mirage-like effect, softening the horizon and making distant cloud edges appear more diffuse. This can add to the feeling that the entire sky is wrapped in a hazy veil, a gentle filter that holds moisture and light in delicate balance. Moisture near the ground and within the cloud also interacts with temperature. When warm, humid air meets a cooler cloud base, water vapor can condense into additional droplets. This enhances the cloud's thickness and, in turn, its capacity to scatter and absorb light. The result is a deeper, more nuanced cloud tone, not merely darker, but more layered. Light becomes an experience of gradients rather than bold contrasts. And as humidity rises further, rain may begin to form within the cloud. The presence of falling droplets adds another layer of soft diffusion, creating those rain curtains that blur light and shape beneath the cloud. So, when we speak of humidity's role in cloud color, we are speaking of something deeply atmospheric. Not just water vapor itself, but the way it alters the very path of light. Not just the cloud's intrinsic properties, but the entire space between the cloud and your eyes. In humid air, the sky feels softer. The light feels gentler. The tones of grey deepen without sharpness, like a watercolor wash across a vast canvas. And as you rest beneath such skies, there is a peaceful quality to the dimmed light, an invitation to slow, to breathe quietly, and to appreciate the subtle interplay of water, air, and illumination. Humidity does not simply make storms look ominous. It makes them look rich, textured, and full of quiet complexity. It is the unseen ingredient that shapes the palette of the sky. A silent conductor in the orchestra of light and shadow, softening, muting, deepening, guiding the way we see the heavens long before the rain begins. When hail forms in a storm, the cloud changes texture and tone. And now, as we drift gently back into the towering canvas of a mature storm, we come to a fascinating blend of water, ice, and light. It is here, high within the cloud, far above the warm surface air, that droplets and ice begin a graceful dance, growing, colliding, freezing, melting, and sometimes forming hail. Let's float among these icy shapes and gently examine their impact on light and shadow. Hailstones are ice spheres that grow inside the strong updrafts of a thunderstorm. These updrafts carry water droplets upward, where temperatures are much colder. In these heights, droplets may freeze into tiny ice crystals. Some stick together, forming larger particles. Others collect additional liquid water that freezes upon their surface in repeated layers. Each cycle adds another thin shell of ice. The process is slow and patient, like layers being painted upon a delicate sphere. Over time, these layers build up into hailstones. Inside the cloud, air motion is constantly moving. Updrafts carry particles upward, while downdrafts pull cooler air downward. Ice crystals and water droplets alike are caught in this invisible circulation. Hailstones may be lifted and dropped multiple times before becoming heavy enough to fall toward the ground. This cycle of lift and descent shapes the way the cloud interacts with light. Ice crystals have a different relationship with light than liquid droplets do. A sphere of water tends to scatter light in many directions, diffusing it gently. Ice, however, especially in crystalline form, refracts and reflects light in more complex ways. Light entering an ice crystal bends and may emerge at a different angle. In some instances, light may be reflected internally before escaping. These interactions cause subtle variations in brightness and tone. At the top of a storm cloud, where ice is abundant, light may be scattered outward, creating the bright, glowing tops we sometimes see from above. Ice crystals catch sunlight strongly, reflecting it back toward the upper atmosphere and into distant horizons. But deeper within the cloud, where hailstones are growing and colliding with droplets, light begins to behave differently. Hailstones are larger than droplets and tend to absorb and scatter light in ways that reduce the amount of direct light passing through. When light encounters a cluster of hailstones, it may be refracted, reflected multiple times, or partially absorbed before it reaches your eyes. This makes the cloud's interior appear more opaque. From below, the presence of hail within a cloud can contribute to a darker base, not because ice is dark in color, but because the complex internal structure of ice and water disrupts light's pathway more thoroughly than droplets alone. Imagine yourself floating within this inner world of mixed ice and water. Light penetrates from above, but its journey is interrupted over and over again. Each ice particle redirects the light. Some rays are sent upward, others sideways. Some are absorbed into the cloud's interior, warming the surrounding air gently. Falling hail adds another layer of shadow. Hailstones, falling through the cloud, create localized regions of higher density. In these regions, light is scattered before it can travel far downward. This contributes to the mottled grey patches you sometimes see at the base of a storm cloud, areas that appear slightly darker because of enhanced scattering and absorption. Hail also influences the dynamic behavior of the storm. As hailstones form and grow, they release latent heat, a gentle transfer of energy that paradoxically warms the air around them, even as they themselves are cold. This release of heat helps sustain updrafts, allowing the storm to reach greater heights and thicker layers. The storm becomes more three-dimensional, and that enhanced depth itself contributes to the way light is blocked and shadowed. So, if rain deepens grey tones in a storm cloud, hail and ice deepen them further, not through fear or intensity, but through complexity. The cloud becomes a tapestry of myriad particles, droplets, ice crystals and hailstones, each bending light, scattering it, absorbing it, redirecting it. This gives the storm a texture that feels heavier to the eye, not because it is dark by nature, but because it is intricately structured, layer upon layer of water in different phases, liquid and solid, soft and hard, each influencing light in its own way. From above, the tops may still gleam brightly in sunlight. Ice crystals shine and reflect. The storm's anvil may glow golden in late afternoon. But below, within the body of the cloud where hail is present, light struggles to penetrate. The base looks deeper grey, more uniform. And as you imagine floating among these icy shapes, you may notice how the storm's tone shifts gently with height, bright and luminous above, softly shadowed in the middle, deepened and opaque below. Hail, ice, and droplets together shape not only precipitation, but also the mood and palette of the storm. They shape how light travels through the cloud and how it reaches our eyes, not in harsh contrast, but in layered subtlety. So, when you see a thunderstorm with hail on the radar, or in distant towering clouds, remember that those icy forms are part of a quiet optical dance: refraction, reflection, absorption, and scattering. A gentle symphony of light interacting with water in all its states. And within that orchestra, the storm cloud reveals its deep, muted tones, beautiful, complex, and quietly sculpted by the very physics of its being. We'll gently approach the stormscapes that sometimes accompany tornadoes, with their dramatic darkness and turbulent bases, always with care, never with fear. And now, as we continue our slow and thoughtful journey through storm clouds and shadowed skies, we come to a type of weather scene that many people recognize instantly. A sky that looks heavier than usual, a cloud base that feels lower, a horizon that seems painted in deeper greys and greens. These are stormscapes that sometimes accompany tornado-producing storms. But tonight, we approach them with softness. We do not rush toward the intense. We simply observe the science behind the atmosphere's most structured storms. Gently, calmly, like watching distant weather through a window. Tornadoes do not appear from every dark cloud, and most storms never produce them. But the storms that can sometimes generate tornadoes often have a distinct appearance, shaped by strong organization within the cloud. These storms are frequently supercells, large, rotating thunderstorms that contain a persistent updraft known as a mesocyclone. The word sounds dramatic, but the concept is simple. The storm's rising air begins to rotate because of wind shear. Wind shear is the change in wind speed or direction with height. When winds at the surface blow one way and winds higher up blow another, the atmosphere begins to twist. If a storm's updraft is strong enough, it can tilt that horizontal twisting motion upward into vertical rotation. And that is how a storm begins to spin. This rotation influences the storm's shape, its structure, and the way its base appears. Often, tornado-bearing storms have a low, broad base. The cloud may appear darker, not because it is more dangerous, but because it is thick with moisture, rain-cooled air, and dense cloud material. The base can be textured, layered, sometimes sculpted into curved bands. One feature often associated with rotating storms is the wall cloud, a lowered, rotating region beneath the storm's main updraft. It forms when warm, moist air is pulled upward, condensing quickly in the lower atmosphere. Because it is closer to the ground and often filled with dense moisture, it can appear especially dark from below. It is not darkness of intention. It is simply thickness, condensation close to the earth, moisture gathering rapidly in the storm's core. Sometimes these stormscapes also contain a rain-free base on one side, where the updraft is strongest and precipitation is held aloft. This can create sharp contrasts, a dark, rotating base on one side and a curtain of rain on the other. The rain curtain itself adds to the storm's dramatic look. Falling rain scatters and absorbs sunlight, creating grey veils and streaks that soften the horizon. Under certain lighting conditions, the storm can take on unusual tones. People sometimes describe the sky as greenish before severe storms. This can happen when sunlight filters through thick storm clouds and interacts with water droplets and ice, scattering light in a way that emphasizes green wavelengths. It is not a supernatural color. It is simply optics. Light passing through a deep, moisture-rich cloud. In these stormscapes, the darkness can feel turbulent because the storm's motion is organized. Air is rising strongly in one region, sinking in another. The base may show swirling scud clouds, low fragments of cloud that form in humid air beneath the storm. These scud clouds can appear to race across the sky, giving the impression of intense movement. But often, they are simply being drawn into the storm's inflow, the stream of warm air feeding the updraft. Everything in the storm is connected. Wind shear shapes rotation. Rotation shapes cloud structure. Moisture shapes darkness. And light shapes the mood. But even as we observe these dramatic skies, we remain calm, because the science itself is steady and understandable. A tornado-bearing stormscape is the result of air masses meeting, winds shifting with height, and strong updrafts organizing the cloud into rotation. It is weather in its most structured form, and from a distance, it can appear like a vast sculpture, layered, textured, shadowed, a storm that seems carved out of air. Tonight, we simply notice its appearance, its broad, dark base, its curved bands, its curtains of rain, its quiet evidence of motion, always with care, never with fear, because even the most dramatic storm skies are still made of the same elements we've been studying all along. Warm air rising, cool air sinking, moisture condensing, light scattering, and darkness forming, not as a warning, but as a natural consequence of depth, density, and structure in the atmosphere. Let's compare slow-moving, layered storm clouds with the towering giants and observe how each wears darkness differently. And now, as our sleepy meteorological journey continues, we step back and look at storms in two different styles. Not every storm cloud rises like a castle. Not every dark sky is built from towering thunderheads. Some storms arrive quietly, in layers, like a soft grey blanket stretched across the horizon. Others rise, suddenly and vertically, reaching high into the atmosphere like mountains of mist. Both can bring shadow. Both can dim the day. But their darkness is shaped in different ways. In meteorology, we often describe these two styles as stratiform and convective. Stratiform clouds are layered. Convective clouds are built upward, and each wears darkness in its own quiet manner. Let's begin with stratiform clouds. Stratiform storm clouds often form when air rises slowly over a broad area, such as along a warm front. The lifting is gentle and widespread. Moisture condenses gradually, producing large sheets of cloud. These clouds often include altostratus and nimbostratus, broad grey layers that can cover the entire sky. Their darkness is even, uniform, soft. Instead of dramatic towers and sharp edges, stratiform clouds offer a continuous ceiling. The sun becomes a pale glow behind them, diffused and muted. Shadows on the ground disappear. The world beneath feels calm and enclosed. Rain from stratiform clouds is often steady and gentle, falling in fine droplets or smooth curtains. The darkness of stratiform clouds comes from thickness spread across a wide area. The cloud layer may not be extremely tall, but it is extensive. Light is scattered repeatedly through the sheet, creating a grey wash that feels constant. Now let's turn to convective clouds. Convective storm clouds form when warm air rises rapidly in columns. Instead of spreading out, the motion concentrates upward. The cloud builds vertically, creating cumulus towers and cumulonimbus giants. Their darkness is often more dramatic. From below, the base of a cumulonimbus can be deep charcoal because it is thick and moisture-rich. But unlike stratiform clouds, convective clouds often show strong contrasts. Their tops may be bright white, catching sunlight. Their edges may glow. Their bases may be dark and textured. They are sculpted rather than uniform. Rain from convective storms often falls in localized shafts. Some areas may receive heavy rain, while nearby regions remain dry. This patchiness creates shifting patterns of shadow on the ground. The darkness of convective clouds comes from depth concentrated in one place. The cloud is tall, dense, and layered vertically. Light enters from above, but struggles to travel downward through miles of moisture. So convective darkness often feels heavier and more defined. Stratiform darkness feels softer and more continuous. One is like a blanket, the other is like a mountain casting shade, and both types can coexist. Sometimes a convective storm can produce a stratiform region, an area of layered rain clouds spreading out behind the main thunderstorm line. This is common in large storm systems, where towering cells feed moisture into broader cloud decks. In these cases, the sky may transition from dramatic towering clouds to a more uniform grey overcast as the storm evolves. This transition is another reminder that storms are living systems, constantly changing form. So when you look up at a dark sky, you can ask gently, is this darkness layered or vertical? Is it a smooth sheet of grey stretching from horizon to horizon? Or is it a towering structure, rising in columns and sculpted edges? Stratiform storms dim the world by covering it evenly. Convective storms dim the world by building deep, shadowed towers. Both are expressions of moisture and rising air, but their personalities are different. One whispers, one stands tall, and yet both can feel strangely soothing when approached with calm observation. Because their darkness is not an enemy. It is simply the absence of direct sunlight, the result of water suspended in air, a reminder that the atmosphere is always shaping light, always reshaping the sky's brightness. So tonight, as we compare these two kinds of storm clouds, we notice how each wears darkness differently. Stratiform clouds, soft, layered, steady grey. Convective clouds, towering, textured, dramatic, shadow. Two styles of dimming, two ways the sky can lower its light, and both, in their own way, invite the world beneath to slow down, breathe gently, and rest under the quiet canopy of weather. As the sun sets, all clouds grow darker, and now, as we drift toward evening, we enter a slower part of the day, one where the world seems to exhale. The bright sharpness of afternoon begins to soften. The air cools gently. Shadows stretch longer across the ground. The sky begins to change its tone. At first, the shift is subtle. The sun is still above the horizon, but its light is no longer as direct. It begins to arrive at an angle, sliding sideways through the atmosphere instead of falling straight down. And with that angle, the light becomes warmer, more golden, more fragile. As the sun sets, all clouds grow darker, but storm clouds hold their shadows longer. This is a quiet truth that you may have noticed without even trying. Thin clouds may fade into pale grey as daylight drains away, but storm clouds, deep, thick, layered, seem to keep their darkness, as if they are made of twilight itself. Tonight, we'll watch the light drain from sky to earth. Imagine standing beneath an open horizon as evening approaches. At first, the clouds overhead still reflect sunlight. Their tops glow softly, their edges catch warm tones. But the underside begins to deepen. As the sun lowers, the light must travel through more atmosphere before it reaches the clouds. Along the way, shorter blue wavelengths scatter away, leaving more reds and oranges. This is why sunsets glow warm, but that warm light is weaker than midday light. It is filtered, softened, thinned, and when it reaches the clouds, it no longer fills them with brightness as easily. Thin clouds still glow for a while because they require little light to appear bright. A small amount of scattered sunlight can still illuminate them. But storm clouds are different. Storm clouds are thick. Their bases are dense with droplets, rain, and sometimes ice. They are already blocking sunlight, even during the day. So, when the sun begins to lower and the light weakens, storm clouds lose their brightness sooner. Their bases become deeper grey. Their shadows stretch across the land more dramatically. And as the sun sinks further, the cloud's interior becomes less illuminated. Light that once bounced through layers of droplets now struggles to enter at all. Storm clouds hold their shadows longer, because they contain more depth. Their thickness acts like a reservoir of darkness. They are built to scatter and absorb light, and so, when light fades, they appear to deepen into shadow more quickly and more completely than smaller clouds. Now we watch the moment when the sun slips close to the horizon. The sky near the sun glows orange and gold, but the opposite side of the sky begins to cool into blue-grey. Storm clouds in that cooler region appear especially dark because they are no longer receiving direct sunlight. They are lit only by diffuse twilight. This is where the world begins to feel truly evening-like. The land beneath storm clouds can become dim even before the sun has fully set, because the clouds intercept the remaining low-angle sunlight. They cast broad shadows that stretch outward like slow-moving blankets. The light drains downward. The brightness leaves the treetops first, then the rooftops, then the streets. The horizon fades, colors soften, and clouds become silhouettes against the last glowing band of sunset. Sometimes, the top of a storm cloud still catches a final touch of sunlight, glowing faintly gold while its base remains dark. This contrast can feel cinematic, like a mountain peak catching the last light of day while valleys below are already in dusk. But soon, even that glow fades, and the storm cloud becomes a quiet shape, a darker mass against the dimming sky. There is something deeply calming about this process, because it is gradual. No sudden switch, no abrupt darkness, just a slow dimming that the body naturally understands. Even without thinking, we feel sleepiness rise as the world darkens. Our nervous system responds to fading light, preparing for rest. Storm clouds intensify that sensation. They deepen the twilight mood. They make the evening feel closer. They hold their shadows longer, because their depth blocks the last remaining sunlight more completely. And as we watch the light drain from sky to earth, we realize that the clouds are not becoming darker in themselves. The droplets have not changed color. The cloud has not become heavier. It is simply that the sun is leaving. The illumination is fading, and the storm cloud, already thick with moisture, becomes one of the first places where daylight disappears. So we rest in this fading moment, watching the last warm light slip away, watching the storm cloud deepen into a soft silhouette, and letting the evening settle gently over the world as the sky becomes quiet and the earth begins its slow drift toward night. We'll explore how storm clouds are not just dark, but tinged with green, blue, silver, and purple. And now, as the sky continues to soften into evening, we look again at storm clouds, not as heavy shapes, not as shadowy ceilings, but as works of colour, because storm clouds are rarely just grey. They carry tones, hints, subtle pigments hidden in their moisture. A storm cloud can appear silver at its edge, blue in its shadow, violet at dusk, or even faintly green under certain conditions. Tonight, we drift through this palette like a bedtime colour wheel. The colours of storm clouds come from light, how it enters the cloud, how it scatters, and what wavelengths reach your eyes. A storm cloud is thick and layered, filled with water droplets, rain, and ice crystals. These particles interact with light in complex ways, scattering it repeatedly and filtering it like a prism made of mist. Let's begin with blue. Blue tones in storm clouds often appear when the cloud is dense and sunlight is limited. In low light, the sky around the cloud may still scatter blue wavelengths, and the cloud's shadowed regions reflect that cool ambient light. The result is a steel blue underside, a calm, muted shade that feels like twilight, even in the middle of the day. Now, purple. Purple and lavender tones often appear during sunset or sunrise. When the sun is low, its warm red-orange light passes through more atmosphere. The blue light scatters away, but some remains in the surrounding sky. When warm and cool light blend together, storm clouds can take on violet hues. Their edges may glow peach, while their interiors deepen into plum and lavender. The storm becomes a painting of warm and cool tones meeting. Now, silver. Silver tones appear when light is diffused. Thin cloud edges or rain curtains can catch soft sunlight and scatter it evenly, creating a metallic sheen. Sometimes, even a dark storm cloud will have a rim of silver along its border, where sunlight strikes its outer droplets. This is called silver lining, and it happens because the cloud's edges are thinner, allowing more light to scatter outward. Silver is the color of light slipping around shadow. Now, green. Green storm clouds are often discussed with curiosity because they can look unusual, almost surreal. The green tint can occur when sunlight filters through a deep storm cloud containing a mixture of water droplets and ice, especially when the storm is tall and thick. The cloud absorbs and scatters red light differently than blue and green light, and the resulting illumination can emphasize green wavelengths. It is not that the cloud is truly green, it is that the light passing through it has been filtered. Often, this happens when the sun is low and shining through the storm, and the cloud's depth acts like a lens of moisture. The world beneath may look tinted, as if seen through green glass. Now, grey. Grey is still the most common tone, but even grey is not a single colour. Storm clouds can hold dozens of greys: pale pearl, slate, charcoal, smoky blue-grey, soft silver grey. Each variation reflects different thicknesses, different droplet sizes, different lighting angles. A storm cloud is textured not only in shape, but in tone. Its base may be dark charcoal because it is thick and rain-filled. Its mid-levels may be softer grey, where light still penetrates. Its top may be bright white, where ice crystals reflect sunlight strongly. And in between, subtle gradients form, like watercolour washes blending from one shade into the next. This is why storm clouds can feel so cinematic. They are not flat objects. They are layered sculptures of moisture and light. They hold multiple colours at once, depending on where the sun is, where the observer is, and how dense each part of the cloud has become. So, when we say storm clouds are dark, we are only saying part of the truth. Storm clouds are deep, yes, but they are also colourful in quiet ways. They contain blues of shadow, silvers of scattered light, purples of evening, and sometimes the strange green glow of filtered sun. And as we rest beneath them, watching their tones shift slowly with time, we can appreciate the storm as a palette, a moving canvas, a sky that paints itself in layers of moisture and light, a bedtime colour wheel turning gently overhead, inviting the world below to soften, dim, and drift peacefully towards sleep. Over oceans or lakes, dark clouds double themselves in reflection. And now, as we continue our gentle weather journey, we drift away from land and toward water. A wide lake, a quiet bay, an open ocean stretching to the horizon. The air here feels different, cooler, smoother, filled with the scent of salt or fresh water, depending on where you are. The surface of the water lies beneath the sky like a second canvas, ready to hold whatever the clouds above decide to paint. And when storm clouds arrive, something beautiful happens. Over oceans or lakes, dark clouds double themselves in reflection. Their shadows are mirrored, their shapes repeated, their tones deepened by the calm surface below. Tonight, we drift gently across water, watching stormlight mirrored. Water is one of the most reflective surfaces in nature, especially when it is calm. When the wind is light, the water becomes glassy, turning into a near-perfect mirror. Even when the surface is rippled, it still catches light in broken fragments, scattering reflections into shimmering patterns. Above the water, storm clouds often appear darker than they do over land. Part of this is because the light environment changes. Over land, sunlight can reflect off buildings, dry ground, sand, or vegetation, sending some brightness upward. But water tends to absorb more light, especially when it is deep. Instead of reflecting a large amount of light upward into the underside of clouds, it often holds that light beneath its surface. So the space between water and cloud can feel dimmer. The storm cloud, already thick and shadowed, appears even darker in contrast to the subdued brightness below. And then comes the reflection. When a storm cloud looms above a lake, its shape is echoed in the water. The dark base becomes a dark patch on the surface, like ink spilled across glass. The anvil top, if bright enough, may appear as a pale smudge of light in the reflection, while the underside becomes a deep grey stain. The storm becomes two storms, one above, one below. The mirrored storm is not as sharp as the real one. Water reflections soften with motion. Waves distort the cloud's edges. Ripples break the shape into fragments, turning it into a shifting mosaic. And yet, the effect is mesmerizing, because reflections amplify mood. A dark cloud over land may feel heavy, but over water it feels expansive. The reflection makes the sky seem larger, the cloud's presence more complete. The storm is no longer just overhead, it is everywhere. If the water is calm, the reflection can be strikingly clear. The horizon line becomes a boundary between two worlds, and the storm seems to stretch endlessly. If the water is rough, the reflection becomes fractured and shimmering. The dark tones flicker and dance, broken into countless moving pieces. Even then, the storm's shadow is visible. It rolls across the surface in slow motion, a drifting darkness that spreads like twilight. Sometimes, when sunlight breaks through the storm, the reflection becomes even more dramatic. A beam of light may strike the water, creating a bright path across the surface. Around it, the storm's reflection remains dark. This contrast, light on water, shadow above, creates a cinematic scene. Water becomes a stage for weather, the sky becomes a painter, and the reflection becomes a second brushstroke. Storms over water also often appear more layered because of the way moisture behaves. Water bodies add humidity to the air through evaporation. This moisture can enhance cloud formation, thickening low layers of mist and haze beneath storm clouds. So the air itself may appear softer, more diffuse. The horizon may fade into grey, and the storm cloud above may seem even deeper in tone. In this setting, light behaves differently. Sunlight filtering through storm clouds may reflect off the water in faint silvers. The underside of clouds may be subtly illuminated by scattered reflections, giving them a smooth, metallic look. Sometimes, the reflection of the storm is darker than the storm itself, because the water absorbs so much light. The mirrored cloud can appear like a deep shadow, even if the cloud above still holds highlights. This doubling creates a quiet visual richness. A storm cloud becomes not only a shape in the sky, but a shape in the world. And as we drift gently across the water in our imagination, we can feel how calming this scene can be. The sky is dim, the water is dark and reflective. The air is cool and moist. The storm's presence is wide, but not urgent. It is simply there, unfolding, a slow-moving shadow, a mirrored ceiling, a cloud doubled into reflection. And beneath it all, the water holds the storm's image like a memory, rippling softly as if the earth itself is dreaming of the sky above. Blue-grey clouds often precede rain, and now, as we return to the land beneath gathering skies, we notice a particular shade that feels familiar. Not charcoal, not bright white, but something softer, a dreamy blue-grey. It is the colour of distant mountains under mist, the colour of twilight in winter, the colour of calm rain approaching slowly across an open field. Blue-grey clouds often precede rain, and they carry a mood that feels quiet and reflective. Tonight, we'll explore how water vapour, thickness, and shadow blend to create their dreamy hue. To understand blue-grey clouds, we begin with the way light behaves in the atmosphere. Sunlight is scattered by air molecules, dust, and water vapour. Shorter blue wavelengths scatter more easily than longer red wavelengths. This is why the clear sky appears blue. Now, imagine a cloud forming in air that is already humid. Water vapour fills the space around the cloud. Tiny droplets may exist in the air even outside the cloud itself, forming haze. This haze scatters light and softens the brightness of the sky. When the sunlight is already diffused by humid air, the cloud's shadowed regions can take on a bluish cast. This is because the cloud is not receiving much direct sunlight from above. Instead, it is lit by ambient light scattered through the surrounding atmosphere. That ambient light is often rich in blue tones, so the cloud reflects what it is given. A muted blue light becomes a muted blue-grey surface. Thickness plays an important role too. A thin cloud often appears bright because sunlight can penetrate and scatter back out. But a thicker cloud blocks direct sunlight. It becomes a barrier, preventing strong illumination from reaching its underside. In this case, the underside is lit mainly by indirect skylight, the diffuse light of the atmosphere. Indirect skylight is cooler in tone, and so the underside becomes cooler in colour. Blue-grey clouds often form in the hours before rain because they are associated with thickening layers of moisture. As a storm system approaches, cloud decks often deepen gradually. Altostratus clouds may spread across the sky, creating a uniform grey layer. As they thicken, they can evolve into nimbostratus, rain-bearing clouds that cover the sky in a smooth sheet. These layered clouds do not always appear purely grey. They often contain subtle blue tones because of the way they filter sunlight. When sunlight passes through thicker clouds, it is scattered and absorbed. The remaining light can be weaker and cooler. The cloud becomes a dim screen between sun and earth, and the world beneath is lit by softer wavelengths. Shadow is another ingredient. When a cloud blocks sunlight, the land beneath becomes shaded. Shaded environments often appear cooler in colour because direct warm sunlight is missing. Our eyes interpret this shade as bluish. This is why shadows on snow appear blue. This is why shaded mountains look blue-grey. And this is why cloud bases can look blue-grey as well. They are shadowed regions, lit primarily by diffuse, cool-toned light. Sometimes, blue-grey clouds are seen in the evening, when the sun is low and the atmosphere scatters more light. In those moments, the warm sunset colours may remain near the horizon, while the overhead sky becomes cooler. The clouds overhead then reflect that cooler sky, appearing blue-grey. And when rain is near, the cloud's moisture content is high. Droplets are abundant. The cloud is thick enough to produce precipitation. That thickness deepens its tone and reduces its brightness. So blue-grey is often the colour of a cloud that is both thick and softly lit. A cloud that is full of moisture but not dramatically towering. A cloud that spreads evenly across the sky, preparing to release rain. There is something deeply calming about this hue. Blue-grey does not feel harsh. It feels quiet. It feels like a softened world, gently muted before rainfall begins. It is the colour of stillness, the colour of air becoming saturated, the colour of the sky lowering its voice. So, when you see blue-grey clouds gathering overhead, you are witnessing a blend of factors. Humid air scattering light, cloud thickness blocking direct sunlight, and shadows creating cooler tones. Water vapour, depth, and diffuse illumination all work together to paint the cloud in its dreamy shade. A gentle sign of rain approaching, not with urgency, not with alarm, but with a slow, steady calm as the atmosphere prepares to let water fall softly back to earth. City lights change the way clouds look. And now, as our gentle journey through the sky continues, we drift away from open fields and quiet coastlines and toward a different kind of landscape, a city at night. Below us, streets form glowing grids. Windows shine like small lanterns. Cars move slowly through avenues, their headlights tracing soft ribbons of white and gold. The city hums quietly beneath the darkness, and above it, clouds gather. But these clouds are not lit only by the moon or stars. They are touched by human light. City lights change the way clouds look because they send illumination upward into the atmosphere. The glow that rises from streets, buildings, and signs reflects off the underside of clouds, painting them in subtle colours. Tonight, let's drift above the glow, exploring how storm clouds wear human light as a faint shimmer. In natural darkness, clouds at night can be difficult to see. Without moonlight, they may blend into the black sky. Their edges soften into invisibility. Their movement becomes subtle, sensed more than observed. But in a city, light pollution transforms the night sky. Artificial light escapes upward because it is not perfectly shielded. Street lamps, billboards, stadium lights, and office towers send photons into the air, where they scatter off dust, aerosols, and moisture. When the air is clear, much of that light disperses upward into the atmosphere, creating the familiar dome of urban glow. But when clouds are present, the effect becomes stronger. Clouds are made of droplets and ice crystals, tiny surfaces that scatter light efficiently. Instead of allowing the light to escape into space, the cloud reflects it back downward and sideways. The underside of the cloud becomes illuminated from below. And so, storm clouds above a city can appear brighter than storm clouds above a rural landscape. They may glow faintly orange from sodium streetlights, or pale white from modern LED lighting. In some cities, they even carry hints of pink, violet, or green, depending on the colour of the artificial lights below. A cloud that might have looked dark and indistinct over a forest becomes visible over a city, glowing like a dim ceiling. But this glow can create the illusion of shadow in a different way. The city beneath may appear darker by comparison, because the clouds reflect light outward and upward, rather than letting it spread evenly across the ground. In some cases, Thick storm clouds can trap light, creating a brighter sky overhead, while the streets below remain oddly dim. It is as if the city has lit its own sky, and the storm cloud has become a reflector. This effect is strongest with low clouds, because the light has a shorter distance to travel before reaching the cloud base. A low cloud deck can glow intensely, almost like a second layer of city lights suspended above the rooftops. Storm clouds, with their dense moisture, reflect even more light. Their bases may shimmer faintly, revealing textures that would be invisible in natural darkness. You may see rolling shapes, soft folds, and slow-moving ripples in the cloud base, lit from below by the city's glow. Sometimes, rain shafts beneath these clouds become visible too. The falling rain catches the artificial light, appearing as faint curtains of silver or grey streaks, drifting downward through the glow. It can look like the sky is dissolving into mist. There is something surreal and cinematic about this. A storm cloud over a city becomes a meeting point between nature and human design. The cloud is still water and air, shaped by wind and convection. But it wears the city's light like a faint shimmer, a soft illumination that does not belong to the cloud itself, but to the world beneath it. This glow can also influence how we perceive the storm's mood. In rural darkness, a storm cloud may feel heavy and unseen, its presence sensed only through wind and distant thunder. But in an urban environment, the cloud becomes visible and textured. It can feel closer, more immediate, because its underside is lit. The city gives the storm a face, and yet the light is gentle. It does not pierce the cloud. It only reflects softly. The cloud remains thick, deep, and full of moisture. It still scatters and absorbs light. It still blocks stars and moonlight above. But below, it becomes a glowing canvas, a dim ceiling painted in amber, ivory, and pale neon hues. So, when you look up from a city street and see storm clouds glowing faintly overhead, you are witnessing a quiet interaction. Artificial light rising upward, scattering through humid air, reflecting off droplets and ice crystals. The storm cloud becomes part of the city's nightscape, a natural structure dressed in human illumination. A reminder that even at night, the sky is never truly dark in the presence of light. And as we drift above the glow, we can rest in this strange, peaceful beauty. Storm clouds wearing the city's shimmer, softly floating above the sleeping streets below. Sometimes, storm clouds aren't darker, just denser against brighter surroundings. And now, as we continue deeper into the dreamy science of storm skies, we return to a theme that has followed us through many chapters: perception. Because the sky is not only what it is, the sky is also what we see. And what we see is shaped by contrast, by context, and by the quiet tricks of the human eye. Sometimes, storm clouds appear darker, not because they have grown dramatically thicker, but because they are framed against brighter regions of sky. We'll ease into the visual illusions of the sky. Imagine a day when the sun is still shining, but a storm cloud approaches from the west. The cloud's base is grey, but not exceptionally so. It is simply a dense cloud, filled with moisture, but nearby, the sky remains bright. Perhaps there is a patch of blue. Perhaps sunlight illuminates a thin layer of cirrus clouds. Perhaps a white cumulus cloud drifts nearby, glowing brightly. Against that brightness, the storm cloud suddenly appears much darker. This is contrast at work. Our eyes do not measure absolute brightness well. Instead, we interpret brightness relative to what surrounds it. A medium grey cloud can look nearly black if it is next to a bright white cloud. The same cloud can look lighter if the entire sky is overcast. So sometimes, what feels like deep darkness is simply a comparison. A cloud does not need to change to appear different. The surroundings change, and the perception changes with them. This is one of the most common optical illusions in storm watching. The cloud looks ominous because it is framed by light. But if the whole sky were evenly grey, the same cloud might look gentle, even soft. Another illusion comes from the way clouds are shaped. A storm cloud often has a flat, dark base. Flat shapes can appear heavier and closer than rounded ones. The underside feels like a ceiling lowered toward the earth, even if the cloud is actually high above. This perceived closeness adds to the feeling of darkness. The mind associates closeness with shadow, with weight, with reduced light. But the cloud's height may not have changed, only its shape has changed. Then there is the illusion created by sunlight angle. When the sun is behind a storm cloud, the cloud becomes backlit. The bright sunlight around the edges creates a halo effect, while the interior becomes a silhouette. This makes the cloud appear darker than it would if the sun was shining directly onto it. It is the same effect as looking at a mountain against the sun. The mountain appears darker because you are seeing it against a bright background. The cloud becomes a silhouette, darkness created by backlighting, not by increased density. There is also the illusion created by rain curtains. Rain falling beneath a cloud can look like part of the cloud itself. From a distance, those grey streaks blend with the cloud base, making the entire structure look darker and heavier. But sometimes, the cloud above may not be especially thick. The rain shaft is what deepens the visual tone. The storm appears darker because you are seeing precipitation as shadow. And finally, there is the illusion created by your own eyes adjusting. As the storm approaches, the light level drops, your pupils widen, your vision shifts. Contrast sensitivity changes. The cloud may appear darker simply because your eyes are now operating in dimmer conditions. So, the storm cloud's darkness can be real, but it can also be amplified by the way we perceive it. These illusions are not mistakes. They are natural features of human sight. Our eyes evolved to detect contrast, to sense changes in brightness quickly, to interpret the environment efficiently, and the sky, with its shifting light and layered moisture, gives our vision plenty to interpret. So, when a storm cloud looks especially dark, it can be helpful to pause and ask gently, is the cloud truly darker, or is it simply framed by brighter surroundings? Is it backlit by the sun? Is rain creating a veil beneath it? Is the cloud's flat base making it feel closer than it is? Is the surrounding sky enhancing the contrast? Often, the answer is a blend of all these factors. Storm darkness is sometimes physical, caused by depth and moisture, and sometimes it is optical, caused by light and perception. The sky is a place where physics and illusion overlap, where water and light create both reality and interpretation. And as we ease into these visual illusions, we can feel how calm it is to understand them. The storm cloud does not need to feel mysterious. It is simply a shape of moisture interacting with light, and our eyes translating that interaction into mood. A gentle reminder that the atmosphere is not only weather, but also art, and that sometimes what looks like darkness is simply the sky playing with contrast, quietly, beautifully, and softly above us. While we see darkness, radar sees inside the storm. And now, as our journey through storm clouds and shadowed skies nears its quiet conclusion, we turn our attention to something human-made, something designed not to replace the beauty of the sky, but to understand it more deeply. Because when we look up at a storm cloud, we see only its surface. We see its charcoal base, its silver edges, its towering shape. We see the way it blocks sunlight and dims the world below. But the storm holds an interior world we cannot see. Inside are droplets colliding, ice crystals swirling, rain forming and falling, updrafts lifting, downdrafts sinking, all of it hidden behind a curtain of cloud. And this is where radar becomes a gentle companion. While we see darkness, radar sees inside the storm. Tonight, we'll softly explore how technology reads cloud density, rain, and shadow. Radar, in its simplest form, is a way of using radio waves to detect objects. Weather radar sends out pulses of energy into the sky. These pulses travel outward, invisible and silent. When they encounter raindrops, snowflakes, hailstones, or even dense cloud particles, some of the energy bounces back toward the radar station. That returned energy is called a reflection or echo. By measuring how much energy returns, radar can estimate how much precipitation is present. Stronger echoes usually mean larger droplets, heavier rain, or hail. This measurement is called reflectivity. Reflectivity is often displayed on radar maps as colors: greens, yellows, oranges, reds, each representing increasing intensity of precipitation. But radar does not see darkness the way our eyes do. Our eyes interpret darkness as a lack of light reaching us. We see a cloud base as dark because sunlight is blocked and scattered. Radar, however, does not care about sunlight. It does not care about shadows. It measures physical particles, water droplets, and ice inside the storm. So, a storm cloud that looks dark may not always have strong radar reflectivity. Sometimes, a cloud can appear dark simply because it is thick and blocking light, even if it is not yet producing heavy rain. And sometimes, a storm can look less dramatic to the eye, while radar reveals intense rainfall hidden within. Radar gives us a different kind of vision, a vision that reads density and structure rather than color. It tells us where rain is falling, where hail might be forming, where the storm's core is strongest. And in many modern systems, radar can even detect motion. This is done using the Doppler effect. Doppler radar measures changes in the frequency of returned waves. If precipitation particles are moving toward the radar, the frequency shifts slightly. If they are moving away, it shifts in the opposite direction. This allows meteorologists to estimate wind motion within storms. It can reveal rotation. It can show outflow boundaries. It can hint at the hidden architecture of the storm's circulation. In a way, radar turns the storm into a transparent object. Not visually transparent, but scientifically readable. The cloud's darkness becomes less mysterious. Its interior becomes a map of moisture and motion. Radar can also detect differences between rain, snow, and hail, because different particles reflect radio waves differently. Hailstones, being larger and denser, often produce strong reflectivity signals. Some radar systems even use dual polarization technology, sending waves in both horizontal and vertical orientations. By comparing how these waves return, meteorologists can infer the shape and type of precipitation. Raindrops tend to be slightly flattened. Snowflakes are irregular. Hailstones are more spherical. Each leaves its own signature. So while our eyes see a storm cloud as a dark ceiling, radar sees it as layers of physical substance. A storm becomes not just a mood in the sky, but a structure filled with measurable particles. And yet, there is something peaceful in this, because radar does not make storms frightening. It makes them understandable. It translates the hidden interior of the cloud into patterns we can interpret. It reads what the cloud is holding, what it is releasing, what it is becoming. So when we see darkness overhead, radar is quietly seeing deeper. It is sensing rain before it reaches the ground. It is tracing the invisible corridors of moisture. It is revealing the storm's secret geometry. And perhaps this is one of the gentle marvels of human curiosity. We build tools not to conquer the sky, but to listen to it more carefully, to see what our eyes cannot, to understand the silent language of water and wind. And as we drift onward through the night, we can imagine radar pulses moving outward like soft ripples in an invisible ocean of air, touching droplets, returning with information, painting a picture of the storm's hidden world, a calm technology reading a calm truth that storms are not only darkness, but structure, motion, and moisture, quietly unfolding behind the veil. In this final chapter, we simply admire the quiet power of a storm cloud's darkness, not as something to fear, but something to behold. And now, as our journey comes to its soft closing, we return to where we began, to the dark cloud, to the shadowed underside of the sky, to that moment when the world dims and the air grows still and the clouds above deepen into grey. So often, we associate darkness with something unsettling, but tonight we choose a different perspective. We choose calm, we choose wonder, we choose to look up and see the storm cloud's darkness not as a warning, but as a kind of beauty, slow, vast, and quietly powerful. A storm cloud's darkness is not emptiness, it is fullness, it is moisture gathered into countless droplets. It is layers of water and ice suspended in air. It is sunlight scattered and softened until only a gentle grey remains. And when we stand beneath it, we are not standing under anger. We are standing under physics, under condensation, under the atmosphere doing what it has always done, moving energy upward, releasing water downward, balancing heat across the planet. A dark cloud is the sky's way of holding water for a moment longer, a calm before the rain, a shade for dreaming. There is something almost comforting about the way a storm cloud dims the world. The bright glare of day fades, harsh shadows disappear. The landscape becomes softer, quieter, muted. Trees look deeper green. Buildings lose their sharp contrast. The horizon becomes hazy. The air feels cool against the skin. And suddenly, everything slows. Even the sounds of the world seem to quiet down. Birds pause. Wind softens. The world listens. This is not because the storm is demanding attention, but because dim light naturally invites stillness. Humans are creatures shaped by sunlight. When light fades, the body begins to rest. The nervous system relaxes. The mind becomes quieter. Storm clouds bring that dimness early, like a gentle evening arriving ahead of schedule. And in that shadow, we can feel safe to soften. We can breathe slower. We can let thoughts drift like mist. A dark cloud is also beautiful in its texture. If you watch closely, you may see soft ripples moving across its base. You may notice gradients of grey shifting slowly as moisture thickens in one region and thins in another. You may see rain curtains hanging like threads. You may see the silver lining at the edge, where sunlight still touches the cloud's outer rim. Even in darkness, there is detail. Even in shadow, there is structure. Storm clouds are sculpted by invisible forces, updrafts lifting moisture, downdrafts sinking cool air, wind shear shaping layers, ice crystals spreading into anvils. The cloud is a living architecture, built from motion, and its darkness is simply the visible result of that architecture becoming deep enough to hold back the sun. There is also a quiet humility in a dark cloud. It reminds us that the atmosphere is vast, that weather is larger than any one moment, that the sky has its own rhythms and cycles, independent of human schedules. A storm cloud does not hurry. It gathers slowly. It releases slowly. It moves onward, shaped by winds we cannot see. And beneath it, we are small, but not insignificant. We are simply part of the same planet that breathes clouds into being. So tonight, we admire the gentle beauty of a dark cloud. We let it be a shade rather than a threat. We let it be a quiet ceiling over the world, a soft grey canopy that invites stillness. We imagine the rain forming above, droplets merging, growing heavy, preparing to fall. We imagine the first drop landing on a leaf, then another, until the world is wrapped in that steady sound that makes everything feel peaceful. And even before the rain begins, the darkness itself is already doing something kind. It is slowing the day. It is cooling the air. It is quieting the landscape. It is offering the earth a moment of rest, a calm before the rain, a pause, a breath, a soft dimming that feels like the sky is tucking the world in. And so, in this final chapter, we simply look up. We let the storm cloud's darkness fill our vision. We let its shadow feel like a blanket. We let its presence remind us that even the heaviest skies are made of softness. Water, air, light, shadow, all blending into one gentle, drifting form. And as the cloud moves overhead and the world grows quiet beneath it, we allow ourselves to drift too, into calm, into stillness, into sleep, under the gentle beauty of a dark cloud. And as our journey winds down, we leave behind the towering clouds and their silver-draped shadows. The sky we explored together, with its drifting greys, its quiet physics, its soft exchanges of light and water, can now slowly fade into the background of your thoughts. The storm clouds we admired are still there somewhere, moving gently across distant horizons. But here, in this moment, there is only stillness. I hope this brought you a sense of calm, and maybe even a new way to see the skies above. Not as something distant or dramatic, but as something patient, something layered, something quietly beautiful in its depth and shadow. If you'd like to support these calming weather journeys, feel free to like or subscribe. Your presence here truly matters. It allows these soft explorations of wind and light to continue drifting outward, like gentle currents in a wide and peaceful sky. Now you can rest. Let your breathing slow, just a little more. Feel the weight of the day settling comfortably away. There is nothing left to understand, nothing left to follow, only the quiet image of a dark cloud moving softly across a fading sky, carrying with it cool air, silver light, and the promise of gentle rain. Feel free to drift into sleep. Let the clouds carry you into dreams. Good night, peaceful dreams, and calm skies to you.